The universe is going dark. Not someday, not in some hypothetical distant future, but right now, as you sit here, galaxies are sliding past a horizon they will never cross again. The light they emit today will never reach us. The space between us and them is stretching faster than their photons can travel, and every second that passes, more galaxies slip beyond that edge, erased not by destruction, but by distance. Cosmologists call this the beginning of the end, the long, quiet countdown to a universe where every galaxy becomes an island, alone in an ocean of nothing, with no way to ever reach another shore. But that is not where this story begins. Because before the darkness comes, before the isolation and the silence, there was an explosion of light so violent and so sudden that it ripped the universe out of total blackness and filled it with 200 billion galaxies, maybe 2 trillion. We are still counting. Each one a cathedral of stars, dust, gas, and something we still do not fully understand holding it all together. And at the center of nearly every one of them, a supermassive black hole, quietly shaping everything around it with gravity so extreme that not even light can resist. This is the full story. From the first galaxies that ignited 13 billion years ago in a universe barely out of infancy, to the Milky Way's 200 billion stars spinning in formation like a cosmic clock, to the collisions that tear galaxies apart and forge new ones, to the final flicker of the last star in a cold, empty, and eternal night. We live in the middle chapter of something unimaginably vast, and no one who understands what comes next can look at the night sky the same way again. This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. The universe has a birthday, not in the way you have a birthday, with cake and candles and embarrassing photos that your relatives dig up at Thanksgiving. The universe's birthday happened roughly 14 billion years ago, and nobody was there to see it. No observers, no cameras, no eyewitnesses. Just energy. An incomprehensible amount of energy packed into a volume smaller than the period at the end of this sentence, and then suddenly not packed anymore, suddenly expanding, suddenly everywhere. We call that moment the Big Bang, which is a terrible name. It wasn't big, it was infinitely small. And it didn't bang. There was no sound because sound requires air, and air requires atoms, and atoms did not exist yet. What happened instead was that space itself began to stretch, carrying energy outward in every direction at once, cooling as it went. And in the first fractions of a second after that expansion began, something called inflation kicked in. A period of exponential growth so rapid that the universe doubled in size more than 60 times over in less time than it takes light to cross the width of a single proton. Inflation smoothed out the wrinkles, flattened the curves, and set the stage for everything that came after. Then it stopped. Just as suddenly as it started, inflation ended, and the universe settled into a more sedate expansion. Still growing, still cooling, but no longer doubling every trillionth of a second. For the next few minutes, the universe was a soup, not a metaphorical soup. An actual, hot, dense plasma of particles smashing into each other at speeds that would make a particle accelerator jealous. Protons and neutrons formed. Electrons appeared. The temperature was high enough that light could not travel more than a few nanometers before slamming into another particle and bouncing off in a different direction. The universe was opaque, a fog of energy so thick that if you could somehow stand inside it, which you could not because you would be vaporized instantly. You would not be able to see your hand in front of your face. Not because it was dark, because it was too bright and too dense, and light simply could not move. This went on for about 380,000 years. 380,000 years of fog. No stars, no galaxies, no structure of any kind. Just a gradually cooling sea of hydrogen and helium nuclei surrounded by electrons, all of it bathed in radiation hot enough to keep everything ionized. And then the temperature dropped below a critical threshold. Protons captured electrons. Neutral hydrogen atoms formed. The fog cleared. Light, for the first time in the history of the universe, could travel freely through space without immediately colliding with something else. Physicists call this moment recombination, which is a confusing name because the electrons and protons were not recombining. They had never been combined in the first place, but the name stuck, and recombination it is. The universe became transparent. That is the phrase the European Space Agency uses, and it is more poetic than they probably intended. For 380,000 years, the universe had been blind to itself, and then suddenly it could see. The light that decoupled from matter at that moment is still traveling. We can still detect it today, stretched by billions of years of cosmic expansion into faint microwave radiation that fills every corner of the sky. We call it the cosmic microwave background, and it is the oldest light in the universe. A photograph of the infant cosmos, frozen at the moment it opened its eyes. But transparent does not mean bright. Once recombination finished and the fog lifted, the universe went dark. Truly dark. No stars had formed yet, no galaxies. The hydrogen and helium drifting through space were neutral, which meant they did not glow. There was nothing to see and no light to see it with. Astronomers call this period the Dark Ages, and the name is not an exaggeration. For tens of millions of years, possibly more than 100 million, the universe was a cold, black, empty void. Neutral hydrogen filled space like an invisible blanket, and nothing disturbed it, except gravity. Gravity does not care whether you can see something. It does not need light or heat or any kind of signal. It just pulls. And in the cooling darkness of the early universe, gravity was already at work. The cosmic microwave background, that snapshot of the universe at 380,000 years old, is not perfectly smooth. If you look closely, there are tiny variations in temperature. Patches that are slightly hotter, patches that are slightly cooler. The differences are minuscule, less than 1 part in 100,000, but they are there. And those tiny ripples were the seeds. Wherever the density was even slightly higher than average, gravity pulled harder. Gas began to drift inward, slowly at first, then faster. The denser a region became, the more strongly it attracted nearby matter, and the process fed on itself. But ordinary matter, the hydrogen and helium we can actually see, was not doing most of the work. Something else was pulling. Something invisible, something that does not emit light or absorb it or interact with anything except through gravity. Dark matter. We still do not know what dark matter is. Decades of experiments have failed to detect a single particle of the stuff directly. But we know it is there because we can see its gravitational effects. Galaxies spin too fast for the visible matter alone to hold them together. Galaxy clusters are heavier than the sum of all the stars and gas we can measure. And in the early universe, dark matter provided the scaffolding, the framework, the skeleton on which everything else could build. Dark matter does not feel pressure the way ordinary matter does. Gas can push back against gravity by heating up, by bouncing particles off each other, by radiating energy away. Dark matter has none of those options. It just collapses. And so, long before any stars formed, the universe was already organizing itself. Invisible halos of dark matter were pulling together, clumping into structures that ranged from a few million times the mass of our sun to billions. These halos sat waiting in the dark like empty nests, and the ordinary matter drifted in to fill them. The first stars did not form for a long time. Estimates vary depending on which model you trust, but most sources place the arrival of the first stars somewhere between 180 million and 300 million years after the Big Bang. That sounds fast when you say it out loud, but it represents a span of time longer than the entire existence of complex life on Earth. The universe spent its infancy in darkness, waiting for something to light the match. When the first stars finally ignited, they were unlike anything that exists today. Population 3 stars, astronomers call them, though the naming convention is backward. Population 1 stars are the youngest, the ones forming now in galaxies like ours, rich in heavy elements. Population 2 stars are older, metal-poor, found in ancient globular clusters. Population 3 stars are the first generation, the ones that formed before any heavy elements existed at all. We have never directly observed a population 3 star. They lived fast and died young, and none of them should still be burning today. But we can model them, and the models all agree on a few basic facts. They were enormous, hundreds of times more massive than our sun, possibly thousands. They burned blue hot, radiating vast amounts of ultraviolet light, and they lived for only a few million years before going supernova. The reason they were so massive has to do with the chemistry, or rather, the lack of it. In the modern universe, when a cloud of gas collapses to form a star, molecules like carbon monoxide and water vapor help cool the gas. Cooler gas fragments more easily, breaking into smaller clumps that become smaller stars. But the early universe had no carbon, no oxygen, no molecules, just hydrogen and helium. Without those cooling agents, the collapsing gas stayed hotter, and hotter gas requires more mass to overcome internal pressure and ignite fusion. The result was a generation of stellar giants, each one a short-lived furnace burning through its fuel in a cosmic blink, and they did more than shine. The ultraviolet light pouring off these first stars was energetic enough to ionize the neutral hydrogen surrounding them. Atoms that had been neutral since recombination were suddenly losing their electrons again, ripped apart by radiation. Bubbles of ionized gas began to form around each star, expanding outward into the darkness. As more stars ignited, more bubbles appeared. Eventually, the bubbles overlapped. The neutral hydrogen fog that had filled the universe for hundreds of millions of years began to burn away, ionized by the collective light of a new generation of stars. Astronomers call this process reionization, and it marked the end of the Dark Ages. The universe lit up, not all at once, but in patches, like streetlights flickering on across a city at dusk. The first stars did something else too. They built the periodic table. Hydrogen and helium are the simplest elements, the ones that formed in the first few minutes after the Big Bang. Everything heavier, everything from carbon to iron to uranium, had to be forged inside stars. The cores of population 3 stars were nuclear reactors, fusing hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into neon, and so on up the chain. When those stars finally ran out of fuel and exploded, they scattered their guts across space. The next generation of stars formed from gas that was no longer pure. It was enriched, contaminated, if you want to be technical, with trace amounts of the elements that would one day make rocky planets possible, the elements that would eventually make you possible. The first galaxies did not form immediately after the first stars. Stars came first, small clumps of them scattered across the universe like embers. But where there were stars, there was gravity, and where there was gravity, more gas flowed in. The dark matter halos that had seeded the first stars kept pulling. More matter arrived, more stars formed. The embers clustered together, building larger and larger structures, proto-galaxies, dwarf galaxies, irregular clumps of stars and gas bound together by gravity, glowing faintly in the dark. The earliest confirmed galaxies we have observed date to roughly 380 million to 400 million years after the Big Bang. That number comes from the James Webb Space Telescope, which was designed specifically to see this far back in time. Before Webb, the record holder sat closer to 450 million years. Webb pushed the frontier earlier, and it keeps finding candidates that sit right at the edge of what should be possible. Galaxies that formed faster, grew larger, and organized themselves more efficiently than the standard models predicted. Some of them rival the mass of the Milky Way, which should not happen. Our galaxy took more than 13 billion years to reach its current size. These early galaxies assembled in less than a billion. The models say that the first matter clumps, the seeds that would grow into galaxies, reached about 10 million solar masses before the first stars ignited inside them. That mass threshold represents the minimum size needed for gas to collapse efficiently into stars under the conditions of the early universe. Anything smaller and the gas would heat up too much, resisting collapse. Anything larger and you start calling it a galaxy. The line between the first star clusters and the first galaxies is blurry because the physics is continuous. One grew into the other without a clear boundary. But somewhere around a few 100 million years after the Big Bang, structures appeared that were unambiguously galaxies. Collections of millions or billions of stars, bound together by dark matter, glowing brightly enough to be seen across the width of the universe. The speed matters. The fact that galaxies formed this quickly tells us something uncomfortable about the early universe. Either gas condensed into stars far more efficiently than it does today, or dark matter halos collapsed faster than the models predicted, or something about the initial conditions, the ripples in the cosmic microwave background, the distribution of matter, the timing of inflation, was tuned in a way that we do not fully understand. The universe had a head start. It began building galaxies almost as soon as the lights came on, and nobody can quite explain why it was in such a hurry. Reionization was not an instant process. It took hundreds of millions of years for the universe to fully transition from neutral to ionized. The first stars created bubbles of ionized gas, but the neutral hydrogen between those bubbles remained dark. Only as more and more stars formed, and as those stars merged into galaxies, and as those galaxies began to interact and collide, did the bubbles finally grow large enough to swallow the remaining neutral regions. By the time the universe was about 1 billion years old, reionization was essentially complete. The fog had lifted for good, the dark ages were over, and the galaxies kept growing. They pulled in more gas. They formed more stars. They collided with their neighbors, merging into larger structures. The early universe was a chaotic place, crowded and violent, with proto-galaxies smashing into each other at rates that would never happen again. Gravity does not stop. Once the first seeds formed, the process became inevitable. Small structures merged into larger ones merged into giants. And at the centers of some of those giants, in the deepest gravitational wells where matter piled up fastest, something even stranger began to form. Black holes, not the small stellar mass kind that form when a single star collapses, supermassive ones. Millions or billions of times heavier than the Sun, sitting at the cores of young galaxies, feeding on the gas and stars around them. growing impossibly large, impossibly fast. That is a different mystery, a different chapter. For now, the point is this. The universe went from nothing to something in less time than it takes a mountain range to erode. 14 billion years sounds like a long time until you realize that the first few 100 million were the most important. That is when the darkness ended. That is when the first light appeared. That is when the cosmic cradle rocked for the first time, and the universe, for lack of a better word, woke up. We are standing at the beginning of a story that ends in silence, but it does not start that way. It starts with a flash. A universe full of hydrogen and hope, gravity pulling matter together, stars igniting, galaxies assembling, and light, finally, traveling freely through space. The first galaxies were small, chaotic, and short-lived. Most of them did not survive. They merged, collided, or were torn apart by their neighbors, but they were the foundation. Every galaxy in the universe today, including the one you are sitting in right now, descends from those first fragile structures, the ones that formed in the dark, lit a match, and refused to go out. And once those first galaxies existed, the universe had options. It had raw material. It had time. It had physics. From here, the story gets complicated. Because the universe did not stop with a handful of proto-galaxies scattered across the void. It built an entire archipelago, billions of islands of stars, separated by oceans of empty space, each one different, each one evolving on its own timeline. That is what comes next. The universe is not empty. That might sound obvious, but it needs to be said because when you look up at the night sky, emptiness is mostly what you see. Black, vast stretches of nothing punctuated by a few thousand visible stars if you are lucky enough to live somewhere without light pollution. The impression you get standing under that sky is that space is a void with a few bright exceptions scattered through it. That impression is completely backward. The universe is full, absurdly full. So full that the human brain cannot hold the number without it sliding off the edges. Start with what we can see. The observable universe, the bubble of space from which light has had enough time to reach us since the Big Bang, spans roughly 93 billion light-years across. That number itself is strange because the universe is only about 13.8 billion years old. You would think the observable universe should be 27.6 billion light-years wide, twice the age of the universe times the speed of light. But the universe has been expanding the entire time that light has been traveling, stretching the distance between us and the objects we are looking at. By the time light from the earliest galaxies reaches Earth, those galaxies are now much farther away than they were when the light left. The observable universe is not a measure of how far light has traveled. It is a measure of how far the objects that emitted that light have moved since then. Inside that bubble, there are galaxies, a lot of them. For decades, astronomers quoted a figure of around 200 billion galaxies in the observable universe. That number came from deep surveys conducted primarily by the Hubble Space Telescope, combined with statistical models that estimated how many faint galaxies existed beyond the detection threshold. 200 billion is already an incomprehensible number. If you tried to count them out loud, one galaxy per second, it would take you more than 6,000 years to finish. But 200 billion turned out to be a significant underestimate. In 2016, a team led by Christopher Consolis at the University of Nottingham reanalyzed decades of deep field data and applied improved modeling techniques to account for galaxies too faint or too distant for current instruments to detect. Their revised estimate came in at roughly 2 trillion galaxies, not 200 billion. 2 trillion, 10 times higher. The paper noted that 90% of the galaxies in the observable universe are currently beyond the reach of even our best telescopes, hidden not because they are too far away in principle, but because they are too faint or too obscured by dust and intervening matter to register clearly. 2 trillion galaxies. If you wanted to visit one galaxy per second, it would take you more than 63,000 years. If every human being alive today adopted a galaxy and took responsibility for studying it, each person would still have to cover roughly 250 galaxies on their own. The scale is so large that it stops meaning anything. Numbers that big do not fit into human experience. They just sit there on the page, inert, waiting for you to move on. The uncertainty around the count is not small. Some estimates push higher, some push lower. The James Webb Space Telescope, which began operations in 2022, has already started refining the census by detecting extremely faint galaxies at distances Hubble could not reach. Every time a new instrument comes online, the count shifts. The 2 trillion figure is not final. It is the best guess we have right now, and it will almost certainly change again in the next decade. What will not change is the basic fact: there are more galaxies in the universe than there are stars in the Milky Way. More galaxies than grains of sand on all the beaches on Earth, if you count generously. More galaxies than seconds in 500,000 years, and they are not all the same. Galaxies come in shapes, sizes, and temperaments. For most of the 20th century, astronomers used a classification system developed by Edwin Hubble in 1926. Hubble, the same astronomer who proved the universe was expanding, also created the tuning fork diagram, a branching chart that sorted galaxies into a few basic types based on their appearance. On one side of the fork, you have spiral galaxies. These are the ones that show up in posters and science fiction movies. Flat rotating disks with bright spiral arms curling outward from a central bulge. Our own Milky Way is a spiral, though we have never seen it from the outside. Spirals tend to be rich in gas and dust, actively forming new stars, and they come in 2 main varieties. Normal spirals have arms that emerge directly from the central bulge. Barred spirals, which make up about 2/3 of all spirals, have a straight bar of stars running through the center, and the spiral arms start at the ends of the bar. The Milky Way is a barred spiral, though we only confirmed that relatively recently by mapping the distribution of stars near the core. On the other side of the tuning fork, you have elliptical galaxies. These are smooth, featureless blobs of stars ranging in shape from nearly spherical to stretched-out footballs. Ellipticals contain mostly old stars and very little gas or dust. Star formation in these galaxies has largely shut down. They are red, dim, and boring to look at, but they can be enormous. The largest known galaxies in the universe are ellipticals, some of them containing trillions of stars, dwarfing anything a spiral could manage. Ellipticals likely form through galaxy mergers. When 2 spirals collide, their orderly structures get scrambled, and what emerges from the wreckage is often an elliptical. Then there are the irregulars, galaxies with no clear structure, no symmetry, no spiral arms or smooth profile, just chaotic clumps of stars and gas scattered across space like someone dropped a bag of marbles. Many irregular galaxies are small, the result of gravitational interactions with larger neighbors that pulled them out of shape. Some are young galaxies that have not yet settled into a stable form. The early universe was full of irregulars. Most of them eventually merged or evolved into spirals and ellipticals, but a few survived into the present day as reminders of what the cosmos used to look like. The Hubble classification is useful, but it is also incomplete. Real galaxies do not always fit neatly into categories. There are lenticular galaxies, which look like spirals that lost their arms. There are ring galaxies, where a circular band of stars surrounds a nearly empty core. There are galaxies with multiple nuclei, galaxies being torn apart by tidal forces, galaxies in the middle of merging with their neighbors. The universe is messier than any diagram can capture. Galaxies are not distributed randomly, they cluster. Gravity pulls them together into groups, and those groups combine into larger clusters, and those clusters link up into superclusters, enormous structures that stretch across hundreds of millions of light years. Our own galaxy, the Milky Way, is part of a small collection called the Local Group. It is not a dramatic name, but it is accurate. The Local Group contains about 80 known galaxies, most of them small dwarf galaxies with only a few billion stars each. The two dominant members are the Milky Way and Andromeda, both large spirals weighing in at several hundred billion solar masses each. The third largest member is Triangulum, another spiral, significantly smaller than the other two. Everything else in the Local Group is a supporting character. Dwarf galaxies orbiting the big ones, irregular clumps drifting through the space between. The Local Group itself sits on the outskirts of the Virgo supercluster, a larger structure containing thousands of galaxies. And the Virgo supercluster is just one lobe of an even larger structure called Laniakea, a supercluster of superclusters spanning more than 500 million light-years and containing the mass of about 100,000 Milky Way-sized galaxies. Laniakea is not held together by gravity in the traditional sense. It is defined by the flow of galaxies through space, the way streams of water converge toward a basin. All the galaxies in Laniakea are drifting in the same general direction, pulled by a massive concentration of matter called the Great Attractor, which sits roughly 200 million light-years away in the direction of the constellations Centaurus and Hydra. We cannot see the Great Attractor directly because it lies behind the plane of the Milky Way, obscured by dust and stars, but we can measure its gravitational influence. Something over there is pulling, and everything in our neighborhood, including us, is moving toward it at about 600 kilometers per second. The cosmic web is the term cosmologists use to describe the large-scale structure of the universe. On the biggest scales, galaxies are not scattered evenly through space. They trace out a network of filaments, sheets and clusters separated by enormous voids. The filaments are like highways of galaxies stretching across hundreds of millions of light-years. The voids are regions where almost nothing exists, gaps in the web tens or hundreds of millions of light-years across, with only a handful of galaxies drifting through them. If you could see the entire observable universe at once, it would look like a three-dimensional spiderweb made of light, with most of the matter concentrated along the threads and vast empty spaces in between. That structure formed because of the same tiny density fluctuations that seeded the first stars and galaxies. Regions that were slightly denser in the early universe pulled in more matter. Regions that were slightly less dense lost matter to their neighbors. Over billions of years, that process amplified itself. The dense regions became filaments and clusters. The underdense regions became voids. Gravity sorted the universe into a foam, and the foam has been growing and evolving ever since. The cosmic web is not static. Filaments are still pulling matter in. Voids are still expanding. Galaxy clusters are still merging. The structure we see today is a snapshot of a process that has been running for more than 13 billion years and will continue for trillions more. Counting galaxies is harder than it sounds. You cannot just point a telescope at the sky and start tallying. Most galaxies are too faint to see without long exposures. Many are hidden behind dust. Some are so far away that their light has been redshifted into the infrared, invisible to optical telescopes. The only way to get an accurate count is to pick a small patch of sky, stare at it for as long as possible, detect every faint smudge of light you can find, and then extrapolate that number across the entire sky. That is exactly what the Hubble Deep Field did. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, seemingly empty patch of sky in the constellation Ursa Major. The patch was only about 1/24 millionth of the entire sky, roughly the size of a tennis ball seen from 100 meters away. Hubble stared at that patch for 10 days, collecting photons, building up an image one layer at a time. When the exposure finished, the image contained about 3,000 galaxies, not stars, galaxies. 3,000 separate islands of billions of stars, most of them so distant that the light had been traveling for billions of years. Some of the galaxies in the image were among the farthest objects ever observed at the time, seen as they existed when the universe was less than 1 billion years old. The Hubble Deep Field was a revelation. It showed that even the darkest, emptiest-looking regions of space are full of galaxies. Everywhere you point a telescope, if you look long enough, galaxies appear. Hubble repeated the experiment several times over the next 2 decades, imaging different patches of sky and pushing the exposure times even longer. The Hubble Ultra Deep Field, released in 2004, stared at a single patch for 11 days and detected about 10,000 galaxies. The Hubble Extreme Deep Field, released in 2012, combined data from more than 2,000 exposures taken over 10 years and pushed even deeper, revealing galaxies so faint they are nearly at the limit of what Hubble can detect. Every time astronomers went deeper, they found more galaxies. The counts kept climbing. The James Webb Space Telescope has taken that process further. Webb's larger mirror and infrared sensitivity allow it to see galaxies that Hubble missed entirely, particularly the very distant ones whose light has been stretched into wavelengths Hubble cannot detect. Webb's deep field images, released starting in 2022, have already identified thousands of new galaxies, many of them at redshifts higher than 13, meaning we are seeing them as they existed less than 400 million years after the Big Bang. Some of these galaxies are so faint that they would be completely invisible to Hubble. Others are bright but heavily obscured by dust, their light absorbed and re-emitted in the infrared where Webb excels. The 2 trillion galaxy estimate is based on this kind of work. Take the number of galaxies detected in deep fields, correct for the ones that are too faint or too distant to see, extrapolate across the entire sky, and the number lands somewhere in the trillions, but the error bars are large. Some models suggest the true number could be lower, closer to 1 trillion. Others push higher, toward 3 trillion or more. The uncertainty reflects the fact that we are trying to count objects we cannot directly observe, using statistical methods to fill in the gaps. Every new deep field observation refines the models, but we are still far from a final answer. One thing the deep fields make clear is that the universe used to be more crowded. When you look at distant galaxies, you are seeing them as they were billions of years ago, and back then, galaxies were closer together. The universe was smaller. The space between galaxies had not yet stretched as much as it has now. Galaxy collisions and interactions were far more common in the early universe than they are today. The Hubble Deep Field images show this. Many of the distant galaxies in those images are irregular, messy, mid-collision. The farther back you look, the more chaotic the universe appears. Spirals are rarer, ellipticals are less common. Most early galaxies look like train wrecks because, in a sense, they were. The Milky Way has been watching you your entire life. Every clear night, if you are far enough from city lights, you can see it. A pale river of light stretching across the sky, so faint that even a street lamp a mile away can wash it out completely. Ancient cultures looked up at that band and saw a road for the dead, a celestial river, a stream of milk spilled by a goddess. The name we use today, Milky Way, comes from the Greek Galaxias Kyklus, meaning milky circle. The Romans called it Via Lactea, the road of milk. Everyone who looked at it knew it was something, but nobody knew what until Galileo pointed a telescope at it in 1610 and realized the pale glow was not milk or mist or divine spill. It was stars. Thousands of them, packed so tightly that their light blended together into a continuous band. We were looking at our own galaxy edge on, from the inside, seeing the combined glow of billions of stars stretching away in every direction. That realization took 300 years to fully sink in. For most of the 1800s, astronomers debated whether the Milky Way was the entire universe, or just one island among many. The question was not settled until the 1920s, when Edwin Hubble measured the distance to Andromeda and proved it was far too distant to be part of our galaxy. The Milky Way was not the universe. It was just one galaxy among billions. A large one, sure, but nothing special. And yet it is the only galaxy we can study from the inside. The only one where we can map individual stars, trace the orbits of gas clouds, measure the thickness of the disk, and watch stars being born in real time. Every other galaxy in the universe is a distant blur, a collection of unresolved light. The Milky Way is home, and home, it turns out, is more complicated than anyone expected. Start with the basics, because even the basics are strange. The Milky Way is a barred spiral galaxy, which means it has a flat rotating disk with spiral arms curling outward from a central bar of stars. That bar is relatively new information. For most of the 20th century, astronomers thought the Milky Way was a normal spiral with arms emerging directly from a central bulge. It was not until the 2000s, using infrared observations that could peer through the dust obscuring the galactic center, that we confirmed the bar. A straight structure roughly 27,000 light-years long, made of densely packed old stars running through the heart of the galaxy like a spoke. Our Sun sits about halfway out from the center, roughly 26,000 light-years away, embedded in one of the spiral arms. We orbit the galactic center at a speed of about 220 kilometers per second. At that speed, it takes us roughly 240 million years to complete one full lap. The last time Earth was in this exact position relative to the galaxy, dinosaurs had not yet evolved. The next time we come around, whatever is left of humanity, if anything, will not recognize the planet. The Milky Way spans about 100,000 light-years from edge to edge, though that number is misleading. The visible disk, the part you can photograph, is only a fraction of the galaxy's total size. Surrounding the disk is a much larger spherical halo of old stars and globular clusters, some of them sitting more than 200,000 light-years from the center. And beyond even that is the dark matter halo, an invisible cloud of gravitating mass that extends outward for hundreds of thousands of light-years, possibly farther. The exact boundary is hard to define because dark matter does not have a sharp edge. It just fades into the space between galaxies, blending into the dark matter filaments of the cosmic web. The galaxy contains somewhere between 100 billion and 400 billion stars, depending on which survey you trust and how you count. The uncertainty is embarrassingly large for something this important, but counting stars in a galaxy you are sitting inside is harder than it sounds. Most of the Milky Way is hidden behind dust. Most of its stars are too faint to detect individually. We can see the bright ones, the giants and supergiants, but the vast majority of stars in the galaxy are dim red dwarfs that barely glow at all. For every star like our Sun, there are dozens of red dwarfs quietly burning through their fuel at a rate so slow they will outlast the current age of the universe. Most of the Milky Way's stars are invisible to us, and the ones we can see are not a representative sample. We are looking at the loudest members of a mostly silent population. The total mass of the Milky Way, including dark matter, is estimated at about 1.5 trillion times the mass of the Sun. Of that, only about 10% is ordinary matter: stars, gas, dust, planets, everything made of atoms. The other 90% is dark matter. We know it is there because the galaxy is rotating too fast. If the only mass present were the stars and gas we can see, the outer regions of the disk would be moving much slower than they actually are. The fact that they are not tells us something invisible is pulling. The rotation curve of the Milky Way, the graph that plots orbital speed against distance from the center, stays flat far beyond the visible edge of the disk. It should drop off. Gravity weakens with distance, so objects farther from the center should orbit more slowly. They do not. The curve stays flat, which means there is mass out there that we are not seeing, a lot of it, enough to dominate the gravitational field of the entire galaxy. Dark matter was first proposed in the 1930s by Fritz Zwicky, who noticed that galaxy clusters were moving too fast to be held together by the visible matter alone. The idea was largely ignored for decades until Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies in the 1970s and found the same problem. Every spiral galaxy they looked at rotated too fast. The only explanation that fit the data was invisible mass, dark matter. It does not emit light, does not absorb light, does not interact with ordinary matter except through gravity. It is only detectable because of what it does to everything around it. The Milky Way, like every other large galaxy, is embedded in a halo of this stuff. The stars and gas we see are just passengers riding on a scaffolding we cannot touch or measure directly. The galaxy exists because dark matter pulled it together. The stars are secondary. The visible part of the Milky Way is divided into three main components: the disk, the bulge, and the halo. The disk is where most of the action happens. It is a thin, flat structure, only about 1,000 light-years thick in most places, filled with gas, dust, and young stars. The spiral arms live here, winding outward from the central bar, in a pattern that looks elegant from the outside, but is deeply confusing from the inside. For a long time, astronomers were not sure how many spiral arms the Milky Way even had. Estimates ranged from 2 to 4. The current consensus, based on infrared surveys from NASA's Spitzer Space Telescope and other instruments, is that the Milky Way has 2 major arms and several smaller ones. The major arms are called Perseus and Scutum Centaurus, and they dominate the structure. The smaller arms, including the one our Sun sits in, are less well defined and may not be true spiral arms at all. They might just be spurs, short offshoots of the main arms, filled with gas and young stars, but not supported by the same density wave mechanics that drive the major arms. Spiral arms are not solid objects. They are not rotating structures made of fixed stars. They are density waves, regions where stars and gas bunch up temporarily as they orbit the galaxy. Think of a traffic jam on a highway. The cars in the jam are constantly changing. Cars enter from behind, slow down, and then accelerate out the front. But the jam itself, the region of higher density, stays in roughly the same place, Spiral arms work the same way. Stars drift into the arm, slow down slightly as they pass through the denser region, and then drift back out. The arm is a pattern, not a thing. It is a wave moving through the disk at a different speed than the stars themselves. The wave is what makes the spiral visible. When gas and dust drift into a spiral arm, they get compressed by the higher density. Compression triggers star formation. Young hot stars ignite, lighting up the arm with intense ultraviolet radiation. Those stars do not live long. Massive stars burn out in a few million years, going supernova and enriching the surrounding gas with heavy elements. By the time a given patch of gas has drifted out of the spiral arm, the bright stars that formed there have already died, and the arm behind them is filled with a new generation of stars formed from gas that just arrived. The spiral pattern persists even though the individual stars creating it are constantly changing. The exact mechanism that creates and maintains spiral density waves is still debated, but the leading theory involves gravitational instabilities in the rotating disk. A small clump of matter, whether stars or gas, creates a gravitational pull that attracts nearby matter. That attraction creates a slightly denser region which pulls even more matter toward it, amplifying the effect. In a rotating disk, those clumps get stretched into spirals by the shearing motion of the galaxy's rotation. The inner parts of the disk rotate faster than the outer parts, so any feature that starts out as a blob gets wound into a curve. Over time, the curves become tightly wound spiral arms. The arms do not last forever. They wind up too tightly and eventually dissolve, only to be replaced by new arms formed by fresh instabilities. The Milky Way's spiral structure is not a permanent feature. It is a dynamic pattern that has existed for billions of years but is constantly renewing itself. Spiral arms are important because they are where stars form. The Milky Way is still actively making new stars, at a rate of about 1 to 3 solar masses per year depending on which estimate you trust. That might not sound like much, but over the galaxy's 13.6 billion year lifetime, it adds up to a significant fraction of the total stellar population. Star formation happens in giant molecular clouds, regions of cold, dense gas where gravity can overcome the internal pressure and collapse the gas into stars. These clouds are enormous, often spanning hundreds of light years and containing hundreds of thousands of solar masses of material. When a spiral density wave passes through one of these clouds, the compression triggers collapse. Stars begin to form in clusters, sometimes hundreds or thousands of them igniting within the same cloud over the span of a few million years. The most massive stars in a cluster burn bright and die fast, exploding as supernovae and blasting the remaining gas out of the region. The lower mass stars survive, drifting apart over time as the cluster dissolves. Our Sun was likely born in a cluster about 4.5 billion years ago, though we have no way of knowing where its siblings ended up. They are scattered across the galaxy now, indistinguishable from any other middle-aged yellow dwarf. The interstellar medium, the gas and dust between the stars, is not empty. It is thin by everyday standards, with a density of about 1 atom per cubic centimeter in the densest regions, and far less than that in the voids between clouds. But spread across the volume of the galaxy, those atoms add up. The Milky Way contains about 10 billion solar masses of gas, most of it hydrogen, along with traces of helium and heavier elements. Dust makes up only about 1% of the interstellar mass, but it has an outsized effect. Dust grains, microscopic particles of carbon, silicon, and other elements, absorb and scatter light. That is why the plane of the Milky Way looks dark in optical images. The dust blocks the light from stars on the far side of the galaxy, making entire regions invisible. Infrared light can penetrate dust more easily, which is why infrared surveys like Spitzer and the James Webb Space Telescope can see through the obscuration and map the structure underneath. The bulge at the center of the galaxy is a different beast. It is a roughly spherical or box-shaped concentration of old stars, densely packed and moving in chaotic orbits rather than the orderly rotation of the disk. The bulge contains some of the oldest stars in the Milky Way, relics from the galaxy's formation more than 13 billion years ago. Star formation in the bulge has largely shut down. There is very little gas left there. Most of it was either turned into stars long ago or blown out by the intense radiation and winds from supernovae and the supermassive black hole at the very center. The bulge is red, dominated by cool old stars that have exhausted most of their fuel and settled into a slow decline. At the exact center of the bulge, buried beneath layers of gas and dust, sits Sagittarius A star, the Milky Way's central supermassive black hole. It weighs about 4.1 million times the mass of the Sun, which makes it middling by supermassive black hole standards. Some galaxies have black holes weighing billions of solar masses. Ours is relatively modest. Sagittarius A star is quiet most of the time. It is not actively feeding on large amounts of matter, so it does not produce the intense radiation that lights up the centers of more active galaxies. We know it is there because we can watch stars orbiting it. Astronomers have been tracking the orbits of stars near the galactic center for decades, and the data clearly show that something extremely massive and extremely compact is sitting at the center of those orbits. The stars come within a few light hours of the black hole, moving at speeds of several percent the speed of light as they whip around the central mass. The only object that can produce that kind of gravitational pull in such a small volume is a black hole. In 2020, the Event Horizon Telescope collaboration released the first direct image of Sagittarius A star, a blurry orange ring of light surrounding a dark central shadow. The shadow is the event horizon, the point of no return where space curves so sharply that even light cannot escape. That image confirmed what decades of indirect observations had already told us. The Milky Way has a black hole at its heart, and that black hole has been there for most of the galaxy's history. The halo is the forgotten component. It surrounds the disk and bulge, a roughly spherical distribution of old stars and globular clusters extending far beyond the visible edge of the galaxy. Globular clusters are tight balls of stars, each one containing hundreds of thousands or even millions of stars packed into a volume only a few dozen light-years across. They are some of the oldest structures in the galaxy, formed more than 12 billion years ago when the Milky Way was still assembling itself from smaller fragments. The stars in globular clusters are metal-poor, meaning they contain very few elements heavier than hydrogen and helium. That makes sense. They formed before generations of supernovae had enriched the interstellar medium with carbon, oxygen, iron, and the rest of the periodic table. Globular clusters orbit the galactic center in highly elliptical paths that take them far out into the halo and then plunge back down through the disk. The Milky Way contains about 150 known globular clusters, though there may be more hiding behind the dust of the galactic plane. The halo also contains streams, long arcs of stars stretched across the sky, marking the trails of dwarf galaxies that the Milky Way has torn apart and absorbed. The Sagittarius dwarf elliptical galaxy is currently in the process of being cannibalized. It has passed through the Milky Way's disk several times over the past few billion years, and each pass strips away more of its stars. Those stars now form a long stream wrapping around the galaxy like a ribbon. Dozens of other streams have been identified, each one the ghost of a smaller galaxy that wandered too close and got shredded by tidal forces. The Milky Way grew by eating its neighbors, and the evidence is scattered across the halo in the form of these stellar streams. Every large galaxy has a history of mergers and acquisitions, and the Milky Way is no exception. The halo is a graveyard. The life cycle of stars inside the Milky Way follows a predictable pattern, though the details vary depending on the star's mass. Stars form in molecular clouds when gravity pulls gas together until the core becomes hot and dense enough for nuclear fusion to ignite. Once fusion starts, the star enters the main sequence, the long, stable phase, where it burns hydrogen into helium in its core. Our Sun is a main sequence star, about halfway through its 10 billion-year lifetime. Lower mass stars, red dwarfs, can stay on the main sequence for trillions of years. Higher mass stars burn through their fuel in a few million years, living fast and dying young. When a star exhausts the hydrogen in its core, it begins fusing heavier elements. Helium fuses into carbon and oxygen. Carbon fuses into neon and magnesium. The process continues up the periodic table, building heavier and heavier elements in layers like an onion. Each stage releases less energy than the one before, and each stage runs faster. A star might spend billions of years fusing hydrogen, a few million fusing helium, and only a few years fusing carbon. By the time it reaches iron, the fusion process stops producing energy. Iron does not release energy when it fuses, it absorbs it. The core collapses, the outer layers rebound, and the star explodes as a supernova. Supernovae are not just dramatic, they are essential. Every element heavier than iron, from cobalt to gold to uranium, is forged in the violence of a supernova explosion or in the collisions of neutron stars. The calcium in your bones, the iron in your blood, the oxygen you are breathing right now, all of it came from stars that died billions of years ago and scattered their enriched gas back into the interstellar medium. That gas, mixed with fresh hydrogen from the cosmic web, collapsed into new molecular clouds and formed new generations of stars and planets. The Milky Way has been recycling its material for more than 13 billion years. The Sun is a third-generation star at least, formed from gas that had already been through multiple cycles of birth, death, and rebirth. The atoms in your body are older than the solar system. They have been part of other stars, other planets, other stories. The Milky Way is not just a collection of stars, it is a vast chemical factory, turning simple hydrogen into the complex elements that make planets and life possible. The interstellar gas is not sitting still. It flows through the disk, pushed by supernova shock waves, pulled by gravity, heated by young stars, cooled by radiation. Gas ejected by supernovae in the disk gets blasted out into the halo, where it cools and eventually falls back down. This cycling process, called the Galactic Fountain, helps regulate star formation across the galaxy. Without it, the Milky Way would have burned through all its gas billions of years ago and shut down. Instead, the gas keeps circulating, feeding new generations of stars, even as old ones die. The Milky Way is not finished. It is still evolving, still changing, still forming new stars and absorbing smaller galaxies. In about 4 billion years, it will collide with Andromeda. The two galaxies are currently approaching each other at about 120 kilometers per second, and their eventual merger is inevitable. When it happens, the collision will scramble both galaxies into a single enormous elliptical. The Sun will likely survive, flung into a random orbit somewhere in the merged remnant. but the night sky will look completely different. If anyone is still around to see it, they will not recognize the Milky Way anymore. It will be gone, absorbed into something larger, its identity erased. That is the fate of every spiral galaxy in the universe. Collide, merge, settle into an elliptical, and wait. The Milky Way is temporary. Every structure in it, every spiral arm, every star cluster, every molecular cloud is part of a story that is still being written but will eventually end. For now, the galaxy is alive. Stars are forming, gas is flowing, spiral arms are winding through the disk, and somewhere near the center, a black hole is waiting. That black hole is not just a curiosity. It is the engine that shaped the galaxy's early history, and it is the key to understanding how galaxies like ours came to exist in the first place. Every large galaxy has one. A supermassive black hole sitting at its core, silent now but once blazingly bright, feeding on the gas and stars around it and pouring energy back into the surrounding space. The Milky Way's black hole is quiet, but it has not always been. And the story of how it got there, how it grew, and what it did to the galaxy around it is the next piece of the puzzle. The Milky Way has a secret at its core, and for most of human history, we had no idea it was there. That is not surprising. The galactic center sits 26,000 light-years away, buried behind layer after layer of gas and dust, so thick that optical telescopes cannot see through it. Point a camera at the center of the galaxy, and all you get is a wall of dark clouds. For centuries, astronomers assumed the center was just more of the same. More stars, more gas, maybe a denser concentration of both, but nothing fundamentally different from the rest of the disk. They were wrong. Sitting at the exact center of the Milky Way, in a region called Sagittarius A star, is an object so dense that its event horizon, the point of no return, where even light cannot escape, spans about 12 million miles. A black hole weighing 4 million times the mass of our Sun. And ours is not special. Nearly every large galaxy in the universe has one of these things sitting at its center. Supermassive black holes. Objects that should not exist, that physics struggles to explain, and that have shaped the evolution of every galaxy they inhabit, including ours. The term supermassive is not hyperbole, it is a technical classification. Stellar mass black holes, the kind that form when a massive star collapses, weigh a few times to a few dozen times the mass of the Sun. Supermassive black holes start at about 100,000 solar masses and go up from there, way up. The Milky Way's black hole is middling. Some galaxies host black holes weighing billions of solar masses. The largest confirmed examples push past 60 billion. 60 billion suns worth of mass compressed into a region smaller than our solar system. If you could somehow replace our Sun with a black hole of the same mass, Earth's orbit would not change. Gravity works the same whether the mass is spread out into a glowing ball of gas or crushed into a singularity. But a supermassive black hole is not just a heavy sun. It is orders of magnitude denser, and its gravitational reach extends across the entire galaxy. Stars near the galactic center orbit the black hole the way planets orbit the Sun, whipping around it at speeds of several percent the speed of light. Those orbits are how we know the black hole is there. No one has ever seen Sagittarius A star directly. Black holes do not emit light. They do not reflect it. They are holes in space where light falls in and never comes back out. The only way to detect them is by watching what they do to everything around them. In the case of Sagittarius A star, the evidence is stars, dozens of them, clustered so close to the galactic center that their orbits can be measured over the span of a human career. Astronomers at the Max Planck Institute for Extraterrestrial Physics in Germany and at UCLA have been tracking these stars since the early 1990s, taking images year after year, watching the stars drift across the sky as they complete their orbits. One star in particular, called S2, has been observed through a full orbit. It takes about 16 years to circle the galactic center, coming within about 11 billion miles of Sagittarius A star at its closest approach. That is roughly the distance from the Sun to Neptune. At that distance, S2 is moving at nearly 2% the speed of light. The only way a star can move that fast is if it is orbiting something extraordinarily massive, packed into an extraordinarily small space. Run the math, and the answer is unambiguous. 4 million solar masses, give or take a few 100,000, concentrated in a region no larger than the orbit of Mercury. The case for Sagittarius A star was not always this strong. In 1971, two astrophysicists named Donald Lyndon Bell and Martin Rees published a paper proposing that a supermassive black hole might sit at the center of the Milky Way. Their reasoning was indirect. Radio galaxies and quasars, objects known to pour enormous amounts of energy into space, seemed to require a central engine capable of converting matter into radiation far more efficiently than any star could manage. The only known mechanism that could do that was accretion onto a black hole. If distant galaxies had supermassive black holes powering their cores, Lyndon Bell and Rees argued, why not ours? The idea was speculative at the time. No one had directly measured the mass at the galactic center. No one had tracked stellar orbits. The suggestion was based on analogy and theoretical reasoning, not hard data. It took another 30 years to confirm they were right. The evidence piled up slowly. Radio observations in the 1970s detected a compact, bright source at the galactic center, later named Sagittarius A star. Infrared observations in the 1980s and 90s, which could penetrate the dust, began to resolve individual stars near the center. By the early 2000s, the orbits were clear enough to calculate the central mass with confidence. In 2020, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, not a photograph in the traditional sense. The image was constructed from radio observations taken by a network of telescopes spread across the entire planet, effectively turning Earth into a single giant dish. What they captured was a blurry ring of orange light surrounding a dark circle. The ring is hot gas spiraling around the black hole, heated to millions of degrees by friction as it falls inward. The dark circle is the shadow of the event horizon, the boundary where space-time curves so sharply that not even light can escape. The shadow is larger than the event horizon itself because the black hole's gravity bends light around it, making it appear bigger than it really is. But the image confirmed what decades of stellar orbit measurements had already told us. Sagittarius A star is real, it is massive, and it is sitting exactly where the models said it should be. Supermassive black holes are not unique to the Milky Way. They appear to be standard equipment in large galaxies. The Hubble Space Telescope has been used to measure black hole masses in dozens of nearby galaxies by observing the motion of stars and gas near their centers. In every case where the measurement could be made, a supermassive black hole turned up. Small galaxies, dwarf galaxies, tend not to have them, or if they do, the black holes are much smaller. But anything larger than a few billion solar masses in stars seems to host a central black hole weighing at least a few million solar masses. The relationship is not random. There is a tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. Bigger bulge, bigger black hole. The ratio sits at about 1 part in 1,000. A galaxy with a bulge weighing 10 billion solar masses typically has a black hole weighing about 10 million solar masses. The relationship is so consistent across different galaxies that astronomers have given it a name, the M-sigma relation. M for black hole mass, sigma for the velocity dispersion of stars in the bulge. The tighter the relationship, the more it suggests that black holes and galaxies did not evolve independently. They grew together. That co-evolution is one of the biggest puzzles in modern astrophysics. Black holes do not just sit passively at the centers of galaxies. They interact with their surroundings in ways that can shut down star formation across the entire galaxy. When gas falls into a supermassive black hole, it does not fall straight in, it spirals. The infalling material forms an accretion disk, a flat rotating structure where gas and dust spiral inward, gradually losing energy to friction and heating up as they go. The inner regions of the disk, the parts closest to the event horizon, reach temperatures of millions of degrees, hot enough to glow in X-rays, hot enough to produce radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. That radiation pours outward, flooding the surrounding galaxy with energy. In extreme cases, jets of matter and energy shoot out along the black hole's rotation axis at speeds approaching the speed of light, punching through the galaxy and extending for hundreds of thousands of light years into intergalactic space. The energy output from an actively feeding supermassive black hole can outshine every star in the galaxy combined. Galaxies with actively feeding black holes are called active galactic nuclei, or AGN. The brightest and most distant examples are called quasars, short for quasi-stellar objects. Quasars were first identified in the 1960s as point sources of light that looked like stars but had extremely unusual spectra. Their light was redshifted, meaning they were extraordinarily distant, and they were shining with a luminosity that no star could match. Some quasars outshine 1 trillion suns. The only explanation that made sense was a supermassive black hole surrounded by a hot accretion disk. Gas falling into the black hole releases gravitational potential energy, converting it into radiation with an efficiency that no other process in the universe can match. Nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. Accretion onto a black hole can convert 10% or more. That is why quasars are so bright. They are the most efficient engines in the universe. Quasars were far more common in the early universe than they are today. When the Hubble Space Telescope and other instruments look at distant galaxies, galaxies so far away that their light has been traveling for billions of years, they find quasars everywhere. The early universe was full of them. Today they are rare. Most supermassive black holes, including Sagittarius A star, are quiet. They are not feeding on large amounts of gas, so they are not producing the intense radiation that lights up a quasar. Sagittarius A star accretes matter at a trickle, a tiny fraction of what it could theoretically consume. That does not mean it is permanently dormant. Evidence suggests that Sagittarius A star was much more active in the past. X-ray observations of gas clouds near the galactic center show signs of illumination by a bright source that is no longer shining. The clouds are glowing in X-rays, but the light is reflected. Something lit them up within the past few hundred years and then turned off. The most likely explanation is a brief flare-up of activity from Sagittarius A star, a burp of radiation as the black hole swallowed a passing gas cloud or star. The flare is over now, but the echoes remain. The question that keeps astrophysicists awake is how supermassive black holes formed in the first place. Stellar mass black holes are straightforward. A massive star runs out of fuel, the core collapses, and a black hole forms. The process takes a few million years from start to finish. Supermassive black holes do not fit that narrative. A black hole weighing a few million solar masses cannot form from a single collapsing star. There is no star that heavy. So where did the seeds come from? There are three main ideas, and none of them are fully satisfying. The first is that the seeds were stellar mass black holes that formed early and then grew by accreting gas and merging with other black holes. Start with a black hole weighing a few dozen solar masses, feed it gas at the maximum rate physics allows, and let it grow for a few billion years. That works in principle, but the math is tight. A black hole accreting at the Eddington limit, the maximum rate at which radiation pressure from the infalling gas does not blow away the surrounding material, doubles its mass roughly every 50 million years. Starting from a stellar mass black hole, you can grow something weighing a few million solar masses in about a billion years. That fits the timeline for nearby galaxies, but it struggles to explain the most distant quasars. The James Webb Space Telescope has detected supermassive black holes weighing hundreds of millions of solar masses in galaxies seen less than a billion years after the Big Bang. If those black holes started as stellar mass seeds, they would have needed to grow at or above the Eddington limit continuously for their entire history. That is possible, but unlikely. Accretion is messy. Black holes do not feed steadily. They eat in bursts, limited by the availability of gas and the chaotic dynamics of the surrounding environment. The second idea is direct collapse. Instead of starting with a stellar mass seed, what if giant clouds of gas in the early universe collapsed straight into black holes without forming stars first? If the conditions were just right, a cloud weighing 100,000 solar masses or more could skip the normal star formation process and collapse directly into a black hole. That would give you a much larger seed to start with, making it easier to grow a supermassive black hole in the time available. The problem is that direct collapse requires very specific conditions. The gas has to stay hot enough to resist fragmenting into smaller clumps, which normally requires a strong source of ultraviolet radiation to keep the gas ionized. Such conditions may have existed in pockets of the early universe, but they would have been rare. Direct collapse is a viable mechanism, but it is not clear whether it happened often enough to explain all the supermassive black holes we see. The third idea is that the seeds were primordial black holes, objects that formed in the first moments after the Big Bang from density fluctuations in the early universe. If primordial black holes existed, they could have been arbitrarily massive, providing ready-made seeds for supermassive black holes. The catch is that no one has ever detected a primordial black hole. The idea is theoretically possible, but there is no direct evidence that they exist. Some researchers take the idea seriously because it solves multiple problems at once. Primordial black holes could explain the rapid growth of early supermassive black holes, and they might also account for some or all of the dark matter in the universe. But without detection, the idea remains speculative. The co-evolution of galaxies and their central black holes is not just a correlation, it is a feedback loop. When a supermassive black hole feeds, it releases energy. That energy heats the surrounding gas, sometimes blowing it out of the galaxy entirely, in winds that travel at thousands of kilometers per second. Those winds can shut down star formation across the entire galaxy by removing the raw material needed to make new stars. Simulations of galaxy formation show that without feedback from supermassive black holes, galaxies would form too many stars too quickly. The simulated galaxies end up with more stars than we observe in real galaxies. Add a central black hole, and the problem goes away. The black hole regulates star formation, keeping the galaxy from growing too large. That regulation appears to be why the M-sigma relation exists. The black hole and the galaxy grow together because the black hole controls how much gas is available for star formation. A bigger black hole produces stronger feedback, limiting the growth of the galaxy. A smaller black hole produces weaker feedback, allowing more stars to form. The two processes balance each other, producing the tight correlation we observe. The most luminous objects in the universe are not stars. They are not supernovae. They are not gamma-ray bursts. They are quasars. The brightest known quasar, a monster called J0100 plus 2802, shines with the light of 400 trillion suns. That luminosity is powered by a black hole weighing about 12 billion solar masses, devouring gas at a rate of roughly 600 Earth masses per day. That is not a typo. 600 Earths worth of matter falling into a black hole every single day. The energy released by that process is so intense that the quasar can be seen across the entire observable universe. If you could somehow stand next to it, which you could not because the radiation would vaporize you long before you got close, the quasar would be brighter than 1 trillion suns packed into a volume smaller than our solar system. The accretion disk around the black hole glows white-hot, and the jets shooting out along the rotation axis extend for millions of light-years, visible in radio wavelengths as enormous lobes of plasma glowing against the darkness of intergalactic space. Blazars are a subset of quasars where one of the jets points almost directly at Earth. When that happens, the jet's relativistic motion amplifies its brightness through a process called Doppler boosting. The result is an object that flickers and flares unpredictably, sometimes doubling in brightness over the course of hours. Blazars are some of the most variable objects in the sky, and they are among the brightest sources of gamma rays. The jets are thought to be powered by magnetic fields twisted and amplified by the rotation of the black hole and the accretion disk. Exactly how the jets form and how they accelerate matter to near light speed is still not fully understood, but the basic picture is clear. Supermassive black holes are not just passive sinks where matter disappears. They are engines. They take gravitational potential energy and convert it into radiation and kinetic energy, pouring that energy back into the surrounding galaxy and sometimes beyond. Sagittarius A star is not doing any of that right now. Our black hole is asleep, or at least dozing. It accretes matter at a rate millions of times lower than the quasars in the early universe. But it was not always this quiet. The Milky Way likely went through an active phase early in its history when Sagittarius A star was feeding heavily and may have been bright enough to qualify as a quasar. That phase ended billions of years ago as the galaxy settled into a more stable configuration and the supply of gas to the central black hole dried up. The gas that remains near the center is diffuse and hot, difficult for the black hole to capture. Most of it ends up in orbits around the black hole rather than falling in. The result is a black hole that sits at the center of the galaxy like a sleeping giant, waiting for the next meal. That meal will come eventually. In about 4 billion years, the Milky Way will collide with Andromeda. The merger will send enormous amounts of gas flooding toward the centers of both galaxies. The two supermassive black holes, ours and Andromeda's, will both light up, feeding on the fresh supply of gas and briefly transforming the merged galaxy into an active galactic nucleus. The collision will also bring the two black holes closer together, and over hundreds of millions of years they will spiral inward, losing energy to gravitational waves until they finally merge into a single black hole weighing about 8 million solar masses. The merger will release a burst of gravitational radiation so powerful that it will ripple across the universe, detectable by any civilization with the right instruments billions of light years away. And then the new black hole will settle down, accreting whatever gas remains nearby, and eventually go quiet again. That is the fate of every supermassive black hole. Periods of intense activity punctuated by long stretches of dormancy, interrupted occasionally by galaxy mergers that stir things up and bring fresh fuel to the center. Supermassive black holes are not destroyers, they are architects. They shape the galaxies around them, regulate star formation, and leave their mark on the structure and evolution of every large galaxy in the universe. The Milky Way would not look the way it does without Sagittarius A star. The bulge, the disk, the rate at which stars form, all of it has been influenced by the presence of the black hole at the center, and every other galaxy tells the same story. Black holes and galaxies grew up together, tangled in a relationship that is still not fully understood, but is clearly fundamental to how the universe organized itself. The black hole is the hidden heart of the galaxy, and it has been beating in its own strange way for more than 13 billion years. That heart is not alone. Across the universe, billions of other galaxies harbor their own supermassive black holes, some quiet like ours, others blazing as quasars, pouring radiation into the void. And those galaxies are not sitting still. They are drifting through space, pulled by gravity, colliding with their neighbors, merging into larger structures. Every collision brings two black holes closer together. Every merger adds mass to the growing monster at the center. The universe is full of galaxies eating each other, and the black holes are along for the ride. Galaxies are not islands. That is the metaphor everyone uses, and it is wrong. Islands sit apart from each other, separated by ocean, stable in their positions for geological timescales. Galaxies do not do that. Galaxies move. They drift through space, pulled by gravity, surrounded by halos of dark matter that extend far beyond their visible edges. And when two galaxies pass close enough, their halos overlap. Gravity takes over. The galaxies do not bounce off each other. They do not politely maintain their distances. They lock together in a slow-motion collision that can take hundreds of millions of years to complete, tearing each other apart, rearranging their stars, triggering bursts of new star formation, and ultimately merging into a single larger structure. The universe is not a collection of isolated objects drifting peacefully through the void. It is a battlefield. Galaxies have been smashing into each other since the first ones formed, and the wreckage is everywhere. The simple answer, according to Christopher Consolis, an astronomer at the University of Nottingham who studies galaxy evolution, is gravity. That is what causes galaxy mergers, gravity and nothing else. Two galaxies do not need to be moving toward each other. They just need to pass close enough that their mutual gravitational pull becomes stronger than the expansion of the universe trying to push them apart. Once that happens, the outcome is inevitable. The galaxies fall toward each other, slowly at first, then faster. Their dark matter halos interpenetrate, and the ordinary matter inside, the stars and gas, begins to respond to the combined gravitational field. Stars that were orbiting one galactic center start feeling the tug of another. Gas clouds that were drifting peacefully through interstellar space get compressed by tidal forces, and the galaxies, despite containing hundreds of billions of stars each, start to merge. The process is not instant. Galaxies are enormous, and even at speeds of hundreds of kilometers per second, it takes a long time for two galaxies to fall together, pass through each other, and spiral back for another collision. The first pass can take tens of millions of years. The galaxies plow through each other, their stars passing like ghosts because the distances between stars are so vast that actual stellar collisions are extraordinarily rare. A galaxy is mostly empty space. Two galaxies can interpenetrate completely without a single star in one galaxy physically hitting a star in the other, but the stars do not need to collide for the interaction to be violent. Gravity does the damage. As the galaxies pass through each other, the gravitational field of each galaxy pulls on the stars of the other, stretching them into long streams and tails that arc away from the collision site. The stars do not stay in their original orbits. They get flung outward, trailing behind the galaxies in graceful curves that can stretch for hundreds of thousands of light years. The gas is a different story. Gas can collide. When two clouds of interstellar gas slam into each other at hundreds of kilometers per second, they do not pass through each other. They compress. Compression heats the gas, but it also increases the density, and higher density means stronger gravity. If the compression is strong enough, the gas collapses, stars begin to form, lots of them. Galaxy mergers are one of the most efficient star formation triggers in the universe. In extreme cases, a major merger can ignite a starburst, a period of runaway star formation where thousands of solar masses worth of new stars form every year. The rate is unsustainable. Starbursts burn through the available gas in a few tens of millions of years, and then they shut down. But while they last, they light up the merger with the combined glow of billions of young hot stars, making the colliding galaxies some of the brightest objects in the sky. The antennae galaxies are the textbook example. Two spiral galaxies, about 65 million light-years away in the constellation Corvus, locked in the middle of a collision. They are named for the two long tails of stars that arc away from the merger site, resembling the antennae of an insect. The tails are tidal streams, composed of stars yanked out of their original galaxies by the gravitational forces of the collision. Each tail stretches more than 300,000 light-years, longer than the diameter of the Milky Way. The galaxies themselves are a mess. The original spiral structures are gone, scrambled by repeated passes. The cores of the two galaxies are still distinct, separated by about 30,000 light-years, but they are spiraling closer together with each orbit. Eventually, within the next few 100 million years, the cores will merge, forming a single elliptical galaxy. The tidal tails will fade as the stars in them gradually fall back toward the merger remnant or drift off into intergalactic space. But the most dramatic feature of the antennae is not the tails, it is the starbursts. Hubble Space Telescope images of the antennae reveal dozens of bright blue knots scattered across the collision zone, each one a superstar cluster, a dense grouping of tens of thousands of newly formed stars packed into a region only a few light-years across. These clusters are forming in real time, triggered by collisions between giant molecular clouds as the two galaxies plow through each other. Some of the clusters are so luminous they outshine entire dwarf galaxies. The antennae are currently forming stars at a rate of about 10 solar masses per year, several times higher than the Milky Way's rate. That might not sound like much compared to the thousands of solar masses per year seen in the most extreme starbursts, but it is enough to be obvious. The collision has turned a pair of ordinary spiral galaxies into a star formation factory, and the process is still ongoing. The Mice galaxies, another nearby pair in the constellation Coma Berenices, show a similar pattern. Two spirals in the process of merging, each one trailing a long streamer of stars pulled out by tidal forces. The nickname comes from the tails, which look like the tails of mice when viewed in wide-field images. The mice are about 300 million light-years away, much farther than the antennae, but the physics is the same. Two galaxies passed close, gravity stretched them into tails, and the collision compressed their gas, triggering star formation. The mice are earlier in the merger process than the antennae. The cores are still relatively intact, and the galaxies have not yet undergone the chaotic scrambling that turns spirals into ellipticals, but they are on the same trajectory. Within a few 100 million years, the mice will complete their merger, and the tails will either fall back into the remnant or dissipate into the space between galaxies. Tidal tails are one of the most recognizable signatures of galaxy mergers, and they are everywhere once you start looking for them. Hubble Deep Field images contain hundreds of examples, galaxies stretched and distorted by gravitational interactions with their neighbors. Some tails are faint and short, barely visible against the background sky. Others are bright and dramatic, extending farther than the galaxies themselves. The tails are not permanent. Stars in tidal streams are moving on elongated orbits that can take hundreds of millions of years to complete. Over time, some of those stars fall back toward the merger site, pulled by the gravity of the remnant. Others drift outward, eventually becoming intergalactic stars, orphaned from their home galaxies and wandering alone through the voids between clusters. The Milky Way's halo contains dozens of stellar streams, long arcs of stars that mark the remnants of dwarf galaxies torn apart and absorbed over the past few billion years. Every tidal tail tells the story of a galaxy that got too close and paid the price. Dynamical friction is the mechanism that ensures mergers complete. When two galaxies pass through each other for the first time, they do not immediately merge. They fall together, interpenetrate, and then separate again, flying apart under the momentum of the initial collision. But they do not escape. Gravity pulls them back. The galaxies fall together a second time, pass through each other again, and separate again. Each pass strips away more of their orbital energy. The mechanism responsible is dynamical friction, a process where the dark matter halos of the two galaxies interact gravitationally, transferring momentum from the galaxies to the surrounding dark matter. The galaxies slow down, their orbits decay. They spiral closer together with each pass, and eventually, after several collisions spread out over hundreds of millions of years, the cores merge. The stars and gas mix together, the two central supermassive black holes sink toward each other, and the merger is complete. The timescale for a full merger depends on the masses of the galaxies and how close they pass on the first encounter. For two large spirals like the Milky Way and Andromeda, the process takes about 500 million years from first contact to final coalescence. Smaller galaxies merge faster because dynamical friction is more efficient when one galaxy is much less massive than the other. Dwarf galaxies falling into the Milky Way can be completely absorbed in a few 100 million years, their stars scattered across the halo, their original identities erased. Major mergers, collisions between two galaxies of comparable mass, take longer because both galaxies have enough mass to resist being torn apart on the first pass. They bounce off each other, regroup, and come back for another round. The merger is a dance, a slow spiral inward, punctuated by violent encounters that reshape both galaxies until there is nothing left to distinguish one from the other. The Milky Way and Andromeda are currently falling toward each other. That is not a prediction, it is a measurement. Andromeda, the nearest large spiral galaxy, sits about 2.5 million light-years away, and it is moving toward us at about 120 kilometers per second. The approach is not random. The Milky Way and Andromeda are the two dominant members of the local group, and their mutual gravity has been pulling them together for billions of years. At current speeds, the two galaxies will begin to merge in about 4.5 billion years. The first pass will stretch both galaxies into tidal tails. The stars in the Milky Way's disk will be scattered, some flung outward into long streams, others pulled inward toward the core. The spiral arms will dissolve. The gas clouds where stars are currently forming will collide with Andromeda's gas, triggering starbursts across the merger zone. And the two supermassive black holes, ours and Andromeda's, will begin the long, slow process of spiraling toward each other, eventually merging into a single black hole weighing about 8 million solar masses. The Sun will almost certainly survive. Stellar collisions are rare even in the densest parts of galaxy mergers because stars are so small compared to the distances between them. The odds of the Sun physically colliding with another star during the Milky Way-Andromeda merger are vanishingly low, but the Sun's orbit will change. Right now, the Sun circles the galactic center in a relatively stable orbit about 26,000 light-years out. After the merger, that orbit will be scrambled. The Sun could end up anywhere in the remnant galaxy, flung into the outer halo, dropped into the core, or left in some intermediate orbit with no resemblance to its current path. The night sky will look completely different. The familiar constellations will be gone, their stars scattered across the merged galaxy. Andromeda, currently a faint smudge visible to the naked eye in dark skies, will loom larger and larger over the course of millions of years, eventually filling a significant portion of the sky as the two galaxies interpenetrate. If anyone is still around to watch, and that is a big if, given that the Sun will be nearing the end of its main sequence lifetime by then, they will witness one of the most dramatic events in the history of the local group. The merger will produce an elliptical galaxy. That is the standard outcome of major mergers between two spirals. Spirals have fragile structures. The flat disks, the spiral arms, the orderly rotation, all of it depends on stars and gas moving in roughly circular orbits around the galactic center. A major merger destroys that order. The stars get scattered into random orbits. The gas either gets consumed in starbursts or blown out of the galaxy entirely by supernova winds and radiation pressure from the newly formed stars. What remains is a smooth, featureless blob of stars moving in chaotic orbits with no net rotation. An elliptical galaxy. The largest elliptical galaxies in the universe, the ones weighing trillions of solar masses and sitting at the centers of galaxy clusters, formed through successive mergers. They started as spirals, collided with their neighbors, merged into ellipticals, and then kept growing by absorbing every smaller galaxy that wandered too close. Ellipticals are the end state of galaxy evolution in dense environments. Once a spiral becomes an elliptical, it does not go back. Galactic cannibalism is the term astronomers use when a large galaxy swallows a smaller one. The process is lopsided. The small galaxy gets torn apart by tidal forces on the first or second pass, its stars scattered into streams that wrap around the larger galaxy. The larger galaxy barely notices. Its stars continue in their orbits, unaffected by the addition of a few billion new stars spread across its halo. The small galaxy's identity disappears. Its stars become part of the larger galaxy's halo population, indistinguishable from stars that have been there for billions of years. The Milky Way is a cannibal. It has eaten dozens of smaller galaxies over its history, and it is in the process of eating several more right now. The Sagittarius dwarf elliptical galaxy is currently being torn apart, its stars stretched into a long stream that loops around the Milky Way multiple times. The Large and Small Magellanic Clouds, two dwarf irregular galaxies visible from the southern hemisphere, are also on a collision course with the Milky Way. They will be absorbed within the next few billion years, Their stars added to the Milky Way's halo, their gas mixed into the disk to fuel future generations of star formation. Minor mergers, interactions between a large galaxy and a much smaller one, are common. One source suggests they may well be a normal part of galaxy life. Galaxies do not grow in isolation. They sit in halos of dark matter that extend far beyond their visible edges, and those halos are constantly pulling in smaller galaxies from the surrounding space. Every large galaxy is surrounded by a swarm of dwarf galaxies, most of them too faint to see without deep imaging. Those dwarfs are not stable. They orbit the larger galaxy, and over time, dynamical friction pulls them inward. Eventually, they fall into the disk or bulge and get absorbed. The process adds mass to the larger galaxy, but it does so gradually without the dramatic fireworks of a major merger. Minor mergers do not trigger massive starbursts. They do not reshape the host galaxy's structure. They just add a bit more mass to the halo and move on. The frequency of galaxy mergers has changed over time. Observations from Hubble and other telescopes show that mergers were far more common in the early universe than they are today. When astronomers look at galaxies at high redshift, galaxies so distant that their light has been traveling for billions of years, they see chaos. Irregular shapes, tidal tails, overlapping galaxies mid-collision. The early universe was crowded. Galaxies were closer together, and the space between them had not yet stretched as much as it has now. Close encounters were inevitable. One estimate suggests that most galaxies in the early universe underwent at least one major merger in their first few billion years of existence. Today, mergers are rarer. One source puts the fraction of nearby galaxies currently involved in interactions at about 5%. The universe has expanded, galaxies have spread out, and collisions are less frequent. But they have not stopped. The Milky Way-Andromeda merger is proof of that. Even in the local universe, galaxies are still colliding, still merging, still reshaping each other through gravity. Mergers are a prediction of lambda CDM, the standard cosmological model. Lambda CDM describes a universe dominated by dark energy and cold dark matter, and it predicts that structure forms hierarchically. Small objects form first, then merge into larger ones. Galaxies grow by absorbing smaller galaxies, which themselves formed by absorbing even smaller clumps of matter. The process is bottom-up, and it has been running since the first dark matter halos collapsed in the early universe. Every large galaxy today is the product of countless mergers stretching back billions of years. The model predicts that mergers should be common in the early universe and less common today, which matches the observations. It predicts that the largest galaxies should sit at the centers of galaxy clusters, which they do, and it predicts that elliptical galaxies should form through mergers, which they clearly do. The evidence is overwhelming. Galaxies are not static, they are dynamic, evolving objects shaped by gravity and interactions with their neighbors. Dark matter plays a critical role in galaxy mergers, even though it is invisible and does not interact with ordinary matter except through gravity. The dark matter halos surrounding galaxies are much larger than the visible galaxies themselves, and when two galaxies collide, their dark matter halos collide first. The halos interpenetrate, and dynamical friction between them slows the galaxies down, ensuring the merger completes. Observations of galaxy cluster collisions have provided some of the strongest evidence for dark matter, by showing that the dark matter and ordinary matter can become separated during a collision. In the Bullet cluster, two galaxy clusters collided at high speed. The galaxies and dark matter passed through each other with little interaction, but the hot gas between the galaxies collided and was left behind at the collision site. Gravitational lensing measurements show that the majority of the mass in the system, the dark matter, is still with the galaxies, while the ordinary matter, the gas, is sitting in the middle where the collision happened. That separation is direct evidence that most of the mass in galaxy clusters is not ordinary matter. It is something else, something invisible, dark matter. Starbursts, triggered by galaxy mergers, can produce thousands of solar masses of new stars per year in extreme cases. Those numbers are rare. Most galaxy mergers have star formation rates well under 100 solar masses per year, which is still higher than the Milky Way's current rate of 1 to 3 solar masses per year, but not wildly so. The extreme cases, the ones producing thousands of solar masses per year, are called ultraluminous infrared galaxies. They are so bright in infrared wavelengths because the intense star formation heats up the surrounding dust, and the dust re-radiates that energy as infrared light. Ultraluminous infrared galaxies are the brightest galaxies in the local universe, outshining normal spirals and ellipticals by factors of 10 or more. They are also short-lived. Starbursts consume gas so quickly that the fuel runs out within a few tens of millions of years. Once the gas is gone, star formation shuts down. The young massive stars that powered the starburst go supernova and die, and the galaxy fades. What remains is an elliptical, red and quiet, filled with old stars and very little gas. Galaxy mergers are not just destructive, they are creative. They trigger star formation, build new structures, mix gas and dust, and ultimately produce the elliptical galaxies that dominate the cores of galaxy clusters. Without mergers, the universe would look very different. Spirals would be more common, ellipticals would be rare. The largest galaxies in the universe would not exist because they only formed by eating their neighbors. Mergers are a fundamental part of galaxy evolution, as important as star formation or supernova feedback. They are the mechanism by which small galaxies grow into large ones, and large ones grow into giants. The collision timescale, the time it takes for two galaxies to fall together and merge, is not short by human standards. 500 million years is longer than complex life has existed on Earth. Longer than the entire Phanerozoic eon, the span of time that includes every fossil you have ever seen in a museum. But by cosmic standards, 500 million years is a blink. Galaxies live for tens of billions of years. A merger that takes 500 million years is a brief, violent episode in an otherwise long and relatively quiet existence. And once the merger is over, once the stars have settled into their new orbits, and the gas has either formed stars or been blown away, the remnant galaxy moves on. It drifts through space, no longer a spiral, no longer two separate objects, but a single elliptical galaxy carrying the combined mass and history of both its parents. The universe is full of these stories. Every elliptical galaxy is a merger remnant. Every tidal tail marks a collision in progress. Every starburst is evidence of gas clouds slamming together at hundreds of kilometers per second. The galaxies we see today are not the galaxies that formed in the early universe. They are the survivors, the ones that grew large enough to avoid being cannibalized, or the products of mergers that combined smaller galaxies into larger ones. Structure in the universe is built through violence. Gravity pulls things together, and when they collide, they do not bounce apart, they merge. And the process repeats, over and over, building larger and larger structures until the expansion of the universe finally pulls everything so far apart that collisions stop. That end is coming. The Milky Way-Andromeda merger will be one of the last major mergers in the local group. After it completes, the remnant elliptical will sit in an increasingly empty region of space as the expansion of the universe accelerates and distant galaxies recede beyond the cosmic horizon. Other galaxies in the local group, the smaller dwarfs and irregulars, will be absorbed over the next few billion years, and then there will be nothing left to merge with. The local group will become a single giant elliptical galaxy, isolated in an expanding universe, with no neighbors close enough to interact with. That isolation is the future for every galaxy not already bound in a cluster. The universe is spreading out, and eventually every galaxy will find itself alone, drifting through an ever-darkening void, with no collisions, no mergers, no new neighbors arriving. The age of galaxy collisions will end, not with a final dramatic merger, but with a slow fade-out as the last interactions play out and the universe grows too large for gravity to pull anything new together. The Milky Way-Andromeda merger will not be the end of anything. It will be a beginning, in a sense, because what emerges from that collision will be larger, heavier, and gravitationally stronger than either galaxy was on its own. The remnant elliptical, sometimes called Milky Way in the popular press, though no astronomer uses that name seriously, will weigh somewhere north of 1 trillion solar masses. It will contain every star from both galaxies, every black hole, every gas cloud that survived the starbursts, and both supermassive black holes fused into one, and it will sit in an increasingly empty region of space, drifting through a universe that is pulling itself apart faster every second. That pulling is not new. The universe has been expanding since the Big Bang, and astronomers have known about it for nearly a century. Edwin Hubble, the same astronomer who proved the Milky Way was not the only galaxy, discovered in 1929 that distant galaxies are moving away from us. Not just a few, all of them. Every galaxy beyond the local group, every cluster, every supercluster, receding into the distance at speeds that increase with their distance from us. The pattern was clear. The farther away a galaxy is, the faster it is moving. That relationship is now called Hubble's law, and it is one of the foundational observations of modern cosmology. Hubble measured the relationship by comparing two numbers for each galaxy: distance and velocity. Distance came from Cepheid variable stars, the same pulsating stars that let astronomers build the cosmic distance ladder. Velocity came from spectroscopy. When a galaxy moves away from you, the light it emits gets stretched by the Doppler effect, shifting toward the red end of the spectrum. The faster the galaxy is receding, the more the light is redshifted. Hubble plotted distance on one axis and velocity on the other, and the points lined up in a straight line. A galaxy twice as far away was moving twice as fast. A galaxy 10 times farther was moving 10 times faster. The relationship was linear, and the slope of that line, the ratio of velocity to distance, became known as the Hubble constant. The number Hubble originally calculated was wildly wrong, off by a factor of about 7, because his distance measurements were systematically too low. But the basic discovery stood. The universe is expanding. Galaxies are not flying away from us because some primordial explosion flung them outward through static space. They are receding because space itself is stretching. The fabric of the universe, if you want to use that metaphor, is being pulled taut, and everything embedded in it is being carried along for the ride. The expansion is happening everywhere at once. There is no center. From any galaxy in the universe, every other unbound galaxy appears to be moving away. The Milky Way is not special. An observer in Andromeda would see the same thing we see. An observer in a galaxy 10 billion light-years away would see the same pattern. Expansion does not have a direction. It is a property of space itself. For most of the 20th century, astronomers assumed the expansion was slowing down. Gravity pulls everything together, and even though the universe is expanding, gravity should be acting as a brake, gradually decelerating the expansion over time. The question was whether the deceleration would be strong enough to eventually halt the expansion and reverse it, causing the universe to collapse back into a big crunch, or whether the expansion would continue forever, slowing asymptotically towards zero but never quite stopping. Both scenarios were consistent with general relativity. The answer depended on the density of matter in the universe. Too much matter and gravity wins. Too little and the expansion continues forever. Astronomers spent decades trying to measure the density with enough precision to tell which scenario was correct. The answer turned out to be neither. In 1998, two independent teams of astronomers studying distant supernovae discovered something no one expected. The expansion of the universe is not slowing down. It is speeding up. Type 1a supernovae, the exploding white dwarfs that serve as standard candles for measuring cosmic distances, were systematically dimmer and therefore farther away than they should have been if the universe were decelerating. The only way to explain the observations was to accept that the expansion rate had increased over the past few billion years. Something was pushing the universe apart, overcoming the attractive pull of gravity and accelerating the expansion. The teams called it dark energy, though the name is a placeholder. Nobody knows what it is. Dark energy is not a substance. It is not made of particles. It does not clump like matter. It does not interact with light or with ordinary matter, except through its effect on the expansion of space. The simplest explanation, and the one that fits the data best, is that dark energy is a property of space itself, a constant energy density that fills every cubic meter of the universe, exerting a kind of negative pressure that pushes space apart. The more space there is, the more dark energy there is, and the stronger the push. As the universe expands, the density of matter drops because the same amount of matter is spread over a larger volume. But the density of dark energy stays constant. Every new cubic meter of space that gets created by expansion contains the same amount of dark energy as every other cubic meter. Eventually, dark energy becomes the dominant component of the universe's energy budget, and from that point on, the expansion accelerates. The current breakdown, based on measurements from the Planck satellite and other sources, puts dark energy at about 72% of the universe's total energy content. Dark matter accounts for about 23%. Ordinary matter, the stuff that makes stars and planets and people, is about 4.6%. We live in a universe dominated by things we do not understand. Dark matter, which we only detect through gravity, makes up about 5 times as much mass as ordinary matter. And dark energy, which we only detect through its effect on the expansion rate, makes up 3 times as much energy as everything else combined. The universe is mostly invisible, and the part we can see is a minority report. The Hubble constant, the number that describes how fast the universe is expanding, is currently measured at about 73 to 74 kilometers per second per megaparsec by local methods. A megaparsec is about 3.26 million light-years. So what that number means is this. For every 3.26 million light-years of distance between us and a distant galaxy, that galaxy is receding an additional 73 kilometers per second faster. A galaxy 10 megaparsecs away is receding at 730 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,300 kilometers per second. A galaxy 1,000 megaparsecs away, about 3 billion light-years, is receding at 73,000 kilometers per second, which is nearly a quarter the speed of light, and the relationship keeps scaling. Far enough away, galaxies are receding faster than light. That last sentence sounds like it violates relativity, but it does not. Nothing is moving through space faster than light. The galaxies themselves are not traveling at superluminal speeds. Space is expanding between us and them, and there is no limit on how fast space can stretch. A galaxy 15 billion light-years away is currently receding from us at more than 3 times the speed of light. Not because it is moving that fast, but because the space between us and it is expanding fast enough that the distance is increasing faster than light could ever cross it. The light that galaxy emitted billions of years ago is still traveling toward us, but the galaxy itself, as it exists right now, is completely unreachable. Even if we could travel at the speed of light, we would never catch it. The space between us is stretching faster than we could ever cross it. That creates a boundary called the cosmic horizon. It is not a physical edge. It is the distance beyond which objects are receding from us faster than light and therefore cannot be observed. Light emitted by a galaxy beyond the cosmic horizon will never reach us. Not because the light stops, but because the space the light has to cross is growing faster than the light can traverse it. The cosmic horizon is currently about 16 billion light-years away, though that number depends on how you define it and what assumptions you make about the future expansion rate. Galaxies beyond the horizon are not visible to us, and they never will be. They are not part of our observable universe. They exist, presumably, but we are cut off from them by the expansion of space itself. The accelerating expansion means the cosmic horizon is not fixed, it is shrinking. Not in the sense that the distance to the horizon is getting smaller. The distance is growing. But the set of galaxies that we can observe is shrinking because more and more galaxies are crossing the horizon as the expansion accelerates. A galaxy that is currently just inside the horizon, its light still able to reach us, will eventually recede past the point where its light can make progress toward us. Once that happens, the galaxy disappears from view, not suddenly. The light that was already on its way continues to arrive, so the galaxy fades gradually over billions of years, its light increasingly redshifted, its apparent brightness dropping until it becomes undetectable, and then it is gone, not destroyed, just isolated, separated from us by a gulf of expanding space that no signal can cross. The local group, the small cluster of galaxies that includes the Milky Way, Andromeda, Triangulum, and about 80 dwarf galaxies, is gravitationally bound. That means the mutual gravity of the galaxies in the group is strong enough to overcome the expansion of space. The local group is not expanding. The galaxies within it are moving toward or around each other, held together by gravity, just like the planets in the solar system are held together by the sun's gravity. The Milky Way and Andromeda are falling together. Triangulum is probably bound to Andromeda. The dwarf galaxies orbit the larger spirals or drift through the space between them. The entire local group spans about 10 million light-years, and as far as the expansion of the universe is concerned, the local group behaves like a single object. It is a bound system, and bound systems do not expand. But the local group is not bound to anything outside itself. The nearest large galaxy cluster, the Virgo cluster, is receding from us. It is about 50 million light-years away, and the space between us and it is expanding. The expansion is slow at that distance, only about 1,000 kilometers per second, so Virgo is still visible. We can still study its galaxies, still measure their properties, still see them as they exist in the relatively recent past. But Virgo is moving away, and over the next tens of billions of years, it will recede farther and farther until it crosses the cosmic horizon and disappears from view. The same is true for the Coma cluster, the Fornax cluster, the Perseus cluster, and every other large structure beyond the local group. They are all receding. None of them are gravitationally bound to us. And as the expansion accelerates, they will all eventually become unreachable. The local group's future, in the context of an accelerating universe, is isolation. The Milky Way and Andromeda will merge into a single elliptical galaxy. The smaller members of the local group, the dwarfs and irregulars, will be absorbed. What remains will be a single massive elliptical sitting in an increasingly empty region of space. The galaxies beyond the local group, the ones we can currently see through telescopes, will fade one by one as they cross the cosmic horizon. Their light will become too redshifted to detect. Their images will freeze in time, showing the galaxies as they looked billions of years ago, because the light from their more recent epochs will never reach us, and eventually the sky will go dark. Not all at once. The process will take trillions of years, but the direction is clear. The universe is pulling itself apart, and the local group is being left behind. There is no center to the expansion. That point is worth repeating, because the mental picture most people carry is wrong. The universe is not expanding outward from a single point the way an explosion expands into empty space. Space itself is stretching uniformly everywhere at once. If you could somehow step outside the universe and watch it expand, you would not see galaxies flying away from a central location. You would see every region of space growing, the distances between all unbound objects increasing at a rate proportional to their separation. An observer in any galaxy, anywhere in the universe, would see the same thing we see. Distant galaxies receding in all directions, their velocities proportional to their distances. The expansion has no preferred direction and no center. Every point in the universe looks like the center from the perspective of an observer at that point. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, is also being stretched by the expansion. When the light from the cosmic microwave background was emitted, about 380,000 years after the Big Bang, it was hot. The photons were in the visible and ultraviolet part of the spectrum, corresponding to a temperature of about 3,000 degrees Kelvin. Over the next 13.8 billion years, the universe expanded by a factor of about 1,000, and the wavelength of those photons stretched with it. Today, the cosmic microwave background is a faint glow in the microwave part of the spectrum, corresponding to a temperature of about 2.7 degrees Kelvin. That is the coldest natural source of light in the universe. It is the afterglow of the Big Bang, stretched and cooled by billions of years of expansion, still filling every corner of the observable universe. As the expansion continues, the cosmic microwave background will keep stretching. Its temperature will drop. Its intensity will fade. In a few 100 billion years, it will be too faint to detect with any conceivable instrument. The universe will still be full of microwave photons, but they will be so diffuse and so cold that they will effectively disappear into the background noise. Future astronomers, if there are any, living in the merged remnant of the local group, will not be able to see the cosmic microwave background. They will not be able to see distant galaxies. Their telescopes will show them a sky filled with the stars of their own galaxy and nothing beyond. The evidence for the Big Bang, the evidence for the expansion of the universe, will be gone. An astronomer in that future universe, trying to figure out the history of the cosmos from observations alone, will have almost no data to work with. The universe will look static, unchanging, and small. Every clue that tells us the universe is vast, ancient, and expanding will have been erased by the expansion itself. Intergalactic space is already mostly empty, and it is getting emptier. The average density of matter in the universe, including dark matter, is about 6 protons per cubic meter. That is an average. In galaxy clusters, the density is higher. In the voids between clusters, the density is lower, sometimes 100 times lower. Intergalactic space contains almost no stars, very little gas, and enormous stretches of nothing. As the expansion continues, the voids will grow. The space between galaxy clusters, already hundreds of millions of light-years across, will stretch to billions of light-years. The space between unbound galaxies will grow until galaxies that are currently neighbors in the same supercluster are separated by distances so vast that light takes billions of years to cross the gap. And because the expansion is accelerating, those gaps will keep growing. The universe is not just getting bigger, it is getting lonelier. The fading of distant galaxies is not hypothetical, it is already happening. Galaxies at high redshift, the ones we see as they existed billions of years ago, are extraordinarily faint. The light from a galaxy at redshift 6, seen as it existed when the universe was less than 1 billion years old, has been traveling for more than 12 billion years. During that time, the universe expanded, and the wavelength of the light stretched with it. The light that left the galaxy in the ultraviolet part of the spectrum arrives at Earth in the infrared. The galaxy's apparent brightness is reduced by the expansion, and its light is spread out over a longer wavelength. Detecting galaxies at redshift 6 requires long exposures with sensitive infrared instruments. Detecting galaxies at redshift 10 or higher, the ones the James Webb Space Telescope is finding, pushes the limits of what current technology can do. The galaxies are still there, they are still emitting light. But the light is so redshifted and so faint that it is barely distinguishable from the background. Now project that forward. A galaxy currently at redshift 6 will, over the next tens of billions of years, recede farther and farther as the expansion continues. Its light will become more redshifted. Its apparent brightness will drop. Eventually, it will cross the cosmic horizon and disappear. The light it emitted before crossing the horizon will continue to arrive for a while, but the light it emits after crossing the horizon will never reach us. The galaxy will freeze in time, and then fade, and then vanish. The same process will play out for every unbound galaxy in the universe. One by one, they will recede beyond the horizon, their light stretching into invisibility, their images locked into the past, until the sky contains nothing but the galaxies in our immediate neighborhood. The Hubble tension, the disagreement between different methods of measuring the expansion rate, is still unresolved. Local measurements using Cepheid variables and Type 1a supernovae give a value around 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background, using data from the Planck satellite, give a value around 67 to 68. The discrepancy is small, only about 8%, but it is persistent and statistically significant. Either one of the methods has an undetected systematic error, or the standard model of cosmology is missing something. Possible explanations include early dark energy, a modification to general relativity, or some other new physics that affects the expansion rate in ways we do not currently understand. The tension has been growing for years, and it shows no sign of resolving itself. Both methods have been refined, both have been cross-checked with independent data, and both continue to give different answers. Something is wrong, but nobody knows what. Dark energy dominates the universe now, and its dominance is only going to increase. In the early universe, matter was the dominant component. The density of matter was higher because the universe was smaller, and gravity was the main force shaping the evolution of structure. Dark energy was always there, but its effect was negligible compared to the gravitational pull of matter. As the universe expanded, the density of matter dropped, but the density of dark energy stayed constant. Eventually, about 4 billion years ago, dark energy overtook matter and became the dominant component. From that point on, the expansion began to accelerate. The shift from deceleration to acceleration is visible in the supernova data. Distant supernovae, seen as they existed more than 5 billion years ago, are slightly brighter than expected because the universe was decelerating at that time and the distances were slightly shorter. Nearby supernovae, seen as they existed within the past few billion years, are dimmer than expected because the universe is accelerating and the distances are slightly longer. The transition point, the moment when dark energy took over, is written into the light curves of exploding stars scattered across billions of light years. The universe does not care about isolation. It does not care that galaxies will lose contact with each other. It does not care that the sky will eventually go dark. The expansion is not a choice. It is a consequence of the Big Bang and the properties of space itself. Dark energy, whatever it is built into the fabric of the universe. It is not something that can be turned off or reversed. The expansion will continue, the acceleration will continue, and the cosmic horizon will continue to shrink. Galaxies that are currently visible will fade and disappear. Galaxies that are currently invisible, already beyond the horizon, will remain invisible forever. The universe is vast now, full of galaxies and clusters and superclusters stretching across billions of light years. But that vastness is temporary. The long-term future of the universe is emptiness. Not the emptiness of a void, the emptiness of isolation. Galaxies separated by such enormous distances that they might as well be alone in the universe. The local group will survive. Bound together by gravity, insulated from the expansion, it will drift through an increasingly dark and empty cosmos. The stars in the merged remnant will continue to shine for trillions of years, slowly exhausting their fuel, one by one winking out as they reach the end of their lifetimes. The gas clouds that currently feed star formation will be consumed, blown away, or locked up in dead stars. New stars will stop forming, the galaxy will age, and as it ages, the universe around it will fade. The distant galaxies, the ones that currently fill deep field images with thousands of pinpoints of light, will recede beyond visibility. The clusters and superclusters that currently trace out the cosmic web will disappear beyond the horizon, and the night sky, for any observers that remain, will show nothing but the stars of their own galaxy and a handful of nearby dwarf galaxies drifting through the void. The expansion is not just taking galaxies away, it is taking information away. The light from distant galaxies carries information about the early universe, about galaxy formation, about the distribution of matter and energy across cosmic time. As those galaxies recede beyond the horizon, that information is lost. The universe is erasing its own history. Future astronomers will not have access to the same data we have. They will not be able to see the cosmic microwave background. They will not be able to observe high redshift galaxies. They will not be able to measure the expansion rate by looking at distant supernovae. The observable universe is shrinking, and the evidence for the Big Bang, for cosmic inflation, for dark energy, is slowly disappearing into the dark. And yet the universe will not be empty. The local group will still be there. The stars will still shine. For trillions of years, the galaxy will be alive, full of light and structure, surrounded by an expanding abyss that grows darker and emptier with every passing eon. The isolation will be complete. No new galaxies will arrive. No signals will come from beyond the horizon. The universe outside the local group will effectively cease to exist, not because it is gone, but because it is unreachable. And in that isolation, the stars will continue their slow march toward extinction, burning through the last of their fuel, one by one going dark, until nothing is left but the cold remnants of a universe that once blazed with light. The universe is not running out of gas, not yet, but it is heading in that direction, and the timeline is surprisingly short by cosmic standards. Galaxies are still forming stars. The Milky Way adds a few solar masses of new stars every year. Other galaxies do the same, some faster, some slower. But the rate is dropping. Star formation across the universe peaked about 10 billion years ago, when the universe was roughly a quarter of its current age. Since then, the rate has been declining steadily. Galaxies are running through their fuel, and the supply is not being replenished fast enough to keep up. The universe is aging, and aging universes make fewer stars. Star formation requires cold gas, specifically cold molecular hydrogen, the kind that clumps together in giant clouds, dense enough for gravity to pull them into collapsing cores that ignite as stars. Without cold gas, nothing happens. The atoms just drift, too hot and too diffuse to collapse. Galaxies are born with enormous reservoirs of hydrogen pulled in from the cosmic web during their formation. That gas settles into rotating disks, cools, and begins forming stars. But once the gas is consumed, either by being turned into stars or by being heated and expelled from the galaxy, star formation shuts down. The galaxy does not die immediately. The stars that have already formed keep shining, some for billions of years, but no new stars appear. The galaxy enters a slow decline, a long fade from active to dormant. There are several ways a galaxy can lose its gas. The simplest is consumption. Stars form, live, and die. Some of that gas gets locked up permanently in stellar remnants like white dwarfs, neutron stars, and black holes. Some gets recycled when massive stars explode as supernovae and blow their enriched guts back into the interstellar medium. But not all of it comes back. A fraction of every generation of stars ends up in compact objects that never return their material to the gas supply. Over billions of years, the reservoir shrinks. The second way is expulsion. Supernova explosions and intense radiation from young massive stars heat the surrounding gas to millions of degrees, hot enough that it can escape the galaxy's gravitational pull entirely. The gas gets blown out into the intergalactic medium, where it drifts for billions of years, too hot and too dispersed to collapse back into the galaxy and form new stars. This process, called feedback, is essential for explaining why galaxies are not more massive than they are. Without feedback, simulations show that galaxies would turn nearly all their gas into stars within a few billion years, producing galaxies far more massive than anything we observe. Feedback regulates star formation by removing the fuel before it can all be consumed. The third way is stripping. When a galaxy falls into a massive cluster, the hot intra-cluster gas, the diffuse plasma filling the space between galaxies in the cluster, exerts pressure on the galaxy's gas as it moves through the cluster. This pressure, called ram pressure stripping, can blow the galaxy's gas out of the disk entirely, leaving the galaxy unable to form new stars. The process is efficient. Galaxies falling into clusters can lose most of their cold gas within a few 100 million years. What remains is a red and dead galaxy filled with old stars and very little gas. Elliptical galaxies in the cores of clusters are almost all gas-poor. They stopped forming stars billions of years ago, and they are not starting again. The fourth way is simply running out of supply. Galaxies pulled gas from the cosmic web during their formation, but that supply is not infinite. the filaments of dark matter and gas that fed galaxies in the early universe are being stretched by the expansion of space. The flow of fresh gas into galaxies has slowed, and in many cases it has stopped entirely. A galaxy that is no longer accreting new gas from its surroundings is living on borrowed time. It will burn through whatever fuel it has left, and then star formation will cease. The overall star formation rate in the universe has been dropping for billions of years, and the trend is accelerating. Observations from Hubble and other telescopes show that the universe formed stars at a rate roughly 10 times higher 10 billion years ago than it does today. The peak occurred around redshift 2, corresponding to a time when the universe was about 3 billion years old. Since then, the rate has been in steady decline. Galaxies are consuming their gas faster than they are replenishing it, and the expansion of the universe is making it harder for new gas to flow in. The universe is not running out of hydrogen. There is still plenty of it floating around in intergalactic space, but it is too hot, too diffuse, and too far from galaxies to collapse and form stars. The raw material is there, but it is no longer accessible. The result is a universe that is slowly fading. Fewer new stars are forming. The brightest, most massive stars, the ones that light up galaxies with their intense ultraviolet radiation, live for only a few million years. As those stars die and are not replaced, the average luminosity of galaxies drops. The galaxies do not go dark immediately. Lower-massed stars, the red dwarfs and yellow dwarfs like our Sun, live much longer, but they are dimmer. A galaxy filled with old low-mass stars is far less luminous than a galaxy with active star formation. Over tens of billions of years, as the massive stars die off and the star formation rate drops to zero, galaxies will become progressively dimmer until they are dominated entirely by the faintest, longest-lived stars. The life cycle of a star depends almost entirely on its mass. Low-mass stars, anything up to about 8 times the mass of our Sun, follow one path. High-mass stars, anything above 8 solar masses, follow another. The dividing line is fusion. A star's core, where nuclear fusion converts hydrogen into helium and heavier elements, can only sustain certain reactions depending on how hot and dense it gets. Low-mass stars do not get hot enough to fuse elements heavier than carbon and oxygen. High-mass stars do. That difference determines everything about how the star dies. Low-mass stars live long, boring lives. Our Sun, a yellow dwarf weighing about 1 solar mass, will spend roughly 10 billion years on the main sequence, the long, stable phase where it fuses hydrogen into helium in its core. It is about halfway through that phase now. Red dwarfs, stars weighing less than half a solar mass, live even longer. The smallest red dwarfs, the ones weighing only about 8% the mass of the Sun, burn their fuel so slowly that they can remain on the main sequence for trillions of years. None of them have died yet. The universe is only 13.8 billion years old, and even the oldest red dwarfs are still burning. They will outlast every other type of star, shining faintly long after everything else has gone dark. When a low-mass star exhausts the hydrogen in its core, fusion stops. The core contracts, heats up, and hydrogen fusion ignites in a shell surrounding the core. The energy from that shell pushes the outer layers of the star outward, swelling the star into a red giant. Our Sun will become a red giant in about 5 billion years, expanding until its outer layers reach roughly the orbit of Mars. The Earth will either be engulfed or scorched into a lifeless cinder. The red giant phase lasts for a few 100 million years, during which the star fuses helium into carbon and oxygen in its core. When the helium runs out, low-mass stars do not have enough gravitational pressure to ignite the next stage of fusion. The core becomes a dense ball of carbon and oxygen, no longer producing energy. The outer layers drift away, forming a glowing shell of gas called a planetary nebula. The name is misleading. Planetary nebulae have nothing to do with planets. Early astronomers thought they looked like planets through small telescopes, and the name stuck. The core left behind is a white dwarf. A white dwarf is roughly the size of Earth, but weighs about half the mass of the Sun. That gives it a density so extreme that a teaspoon of white dwarf material would weigh up to 100 metric tons, according to ESA. White dwarfs are not stars in the traditional sense. They are not fusing anything. They are just hot, dense spheres of carbon and oxygen, supported against gravity by electron degeneracy pressure, a quantum mechanical effect that prevents the electrons in the core from being compressed any further. A white dwarf does not collapse into a black hole because the electrons, packed as tightly as physics allows, push back against gravity just hard enough to maintain equilibrium. White dwarfs do not shine by fusion. They shine because they are hot, and they cool over billions of years by radiating their stored thermal energy into space. A freshly formed white dwarf can have a surface temperature of 100,000 degrees Kelvin, hot enough to glow brilliant white or even blue. Over time, the temperature drops. After a few billion years, the white dwarf cools to a few thousand degrees, glowing a dull red. After tens of billions of years, it cools further, fading into the infrared and eventually becoming too dim to detect. The final state is a black dwarf, a cold, dark lump of carbon and oxygen drifting through space, no longer emitting any detectable light. No black dwarfs exist yet. The universe is not old enough. The oldest white dwarfs, formed in the first generation of stars more than 13 billion years ago, are still glowing faintly in the red and infrared. It will take another several trillion years for the first black dwarfs to appear. White dwarfs are stable. They can sit in space for trillions of years, cooling slowly, unbothered by anything except the occasional close encounter with another star or the slow decay of the protons in their cores, a process so slow that it may never happen within the lifespan of the universe. White dwarfs are the endpoint for the vast majority of stars. Our Sun will become one. Most of the stars in the Milky Way will become one. In a few trillion years, after the last low-mass stars have exhausted their fuel and shed their outer layers, the universe will be filled with white dwarfs, billions upon billions of cooling embers, slowly fading into invisibility. High-mass stars do not get that luxury. They live fast and die violently. A star weighing 10 times the mass of the Sun burns through its hydrogen in only about 10 million years, 1,000 times faster than the Sun. When the hydrogen runs out, the core contracts and heats up enough to fuse helium into carbon and oxygen. When the helium runs out, the core contracts again and fuses carbon into neon and magnesium. The process continues, building heavier and heavier elements in concentric shells like layers of an onion. Neon fuses into oxygen, oxygen fuses into silicon, silicon fuses into iron. Each stage runs faster than the one before. A star might spend 10 million years fusing hydrogen, 1 million years fusing helium, 1,000 years fusing carbon, and only a few days fusing silicon into iron. The progression is relentless, driven by gravity pulling the core inward and fusion pushing back. But fusion only pushes back as long as it releases energy. Iron is the breaking point. Iron nuclei are the most stable nuclei in the universe. Fusing iron into anything heavier does not release energy. It absorbs energy. When the core of a massive star becomes mostly iron, fusion stops. The core is no longer producing heat, and without heat, there is no outward pressure to resist gravity. The core collapses, not slowly. The collapse happens in less than a second. The iron core, roughly the size of Earth, implodes, its electrons and protons crushed together so tightly that they combine into neutrons. The core becomes a ball of neutrons about 20 kilometers across, held up by neutron degeneracy pressure, the same quantum mechanical effect that supports white dwarfs, but operating at a higher density. The collapse releases an enormous amount of gravitational potential energy, and most of that energy goes into blowing the outer layers of the star apart in a supernova explosion. A core collapse supernova is one of the most energetic events in the universe. For a few weeks, the exploding star can outshine its entire host galaxy. The explosion ejects a cloud of debris, a supernova remnant, expanding outward at thousands of kilometers per second. That debris is enriched with heavy elements forged in the core and during the explosion itself. Every element heavier than iron, from cobalt to gold to uranium, is created in supernova explosions or in the collisions of neutron stars. The remnant expands for thousands of years, eventually mixing with the interstellar medium and seeding it with the elements needed to form the next generation of stars and planets. The Sun and Earth are made of supernova debris. Every atom heavier than helium in your body was forged in a star that died before the solar system formed. The core left behind is either a neutron star or a black hole. The dividing line is mass. If the core weighs more than about 3 solar masses, neutron degeneracy pressure is not enough to stop the collapse. The core keeps collapsing, shrinking past the point where any known force can resist gravity, and it becomes a black hole, a region where space-time curves so sharply that not even light can escape. The event horizon, the boundary where escape velocity equals the speed of light, forms around the collapsed core, and everything inside is lost to the outside universe. NASA describes black holes as objects whose gravity is so strong that light cannot escape once material crosses the event horizon. That is accurate, but it undersells the strangeness. A black hole is not an object in the traditional sense. It is a hole in space-time, a place where the fabric of the universe has been torn by gravity. Matter that falls in does not sit on a surface. It falls toward the singularity at the center, a point where density becomes infinite and the laws of physics break down. We do not know what happens there. General relativity predicts the singularity, but it also stops working at that point. The equations produce infinities, which is a physicist's way of saying the theory is incomplete. If the core weighs less than about 3 solar masses, the collapse stops at the neutron star stage. Neutron stars are extraordinarily dense. A neutron star with a mass of about 1.4 times the Sun weighs roughly as much as the Sun, but is compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is intense enough that anything falling onto a neutron star hits with enough energy to trigger nuclear reactions. Neutron stars spin rapidly, often completing hundreds of rotations per second, and many of them have intense magnetic fields. Some neutron stars emit beams of radiation along their magnetic poles, and if those beams sweep past Earth, we detect them as pulsars, rapidly pulsing sources of radio waves or X-rays. Pulsars are extraordinarily precise clocks. The rotation period of some pulsars is stable to better than 1 part in a billion, making them more accurate than the best atomic clocks on Earth. Neutron stars do not last forever. They cool over time, just like white dwarfs, radiating away their thermal energy until they become too cold to emit detectable radiation. The timescale is shorter than for white dwarfs because neutron stars are smaller and have less thermal mass, but it is still billions of years. Eventually, neutron stars fade into invisibility, becoming cold, dark objects drifting through space. Black holes, by contrast, do not cool in the traditional sense. They do not emit thermal radiation. They do emit something called Hawking radiation, a quantum mechanical process predicted by Stephen Hawking in the 1970s. Hawking radiation is extraordinarily weak for stellar mass black holes. A black hole weighing 10 solar masses has a temperature of about 6 billionths of a degree above absolute zero, far colder than the cosmic microwave background. Such a black hole absorbs more radiation from the universe than it emits, so it grows rather than shrinks. Only in the far future, after the cosmic microwave background has cooled below the Hawking temperature of the black hole, will the black hole begin to lose mass. The process is slow. A stellar mass black hole would take 10 to the 67 years to evaporate completely, a timescale so long that it makes the current age of the universe look like a rounding error. Over time, galaxies become repositories of dead stars, white dwarfs, neutron stars, black holes. The bright, massive stars that currently dominate the luminosity of galaxies will all die within a few tens of millions of years. The lower mass stars will follow over billions of years. Eventually, the only stars left shining will be the longest-lived red dwarfs, and even those will exhaust their fuel after trillions of years. What remains is a graveyard, a galaxy filled with stellar corpses, faintly glowing or completely dark, drifting through space in orbits that gradually decay as gravitational interactions and dynamical friction sap their energy. Star clusters, the tightly bound groups of stars that formed together in the same molecular cloud, do not last forever. Open clusters, loose associations of a few hundred to a few thousand stars, disperse relatively quickly on cosmic timescales. Gravitational interactions with passing stars and gas clouds gradually pull the cluster apart. Most open clusters dissolve within a few 100 million years, their stars scattered across the galaxy, indistinguishable from the general stellar population. The Pleiades, a young open cluster visible to the naked eye, will not exist as a recognizable cluster in another few 100 million years. Its stars will drift apart, absorbed into the disk of the Milky Way. Globular clusters are more resilient. These are ancient, tightly bound spheres of hundreds of thousands or even millions of stars, orbiting the galactic center in the halo. Globular clusters formed more than 12 billion years ago, and most of them have survived to the present day, but they are not permanent. Over billions of years, gravitational interactions between stars in the cluster cause some stars to gain energy and others to lose it. The stars that gain energy get kicked out of the cluster entirely, escaping into the halo. The stars that lose energy sink toward the center, where the density is highest. Over time, the cluster loses mass from its outer regions and becomes more concentrated at its core. The process is called evaporation, and it is the eventual fate of every star cluster. Given enough time, tens or hundreds of billions of years, even the most massive globular clusters will evaporate completely, their stars dispersed into the halo. Some globular clusters undergo a more dramatic end. If the core becomes dense enough, stars collide and merge, building up a central concentration of mass that can collapse into an intermediate mass black hole. The black hole then grows by accreting nearby stars and eventually swallows a significant fraction of the cluster's mass. The remaining stars are either ejected or fall into the black hole. The cluster does not so much evaporate as get eaten from the inside out. The timescales are long, but the outcome is inevitable. Every bound system of stars will eventually unbind or collapse. Nothing lasts. Planetary nebulae, the glowing shells of gas ejected by dying low-mass stars, fade relatively quickly. The gas expands outward, driven by the radiation pressure from the hot white dwarf at the center. After a few thousand years, the shell becomes too diffuse to glow brightly, and after a few tens of thousands of years, it merges with the surrounding interstellar medium and disappears. Planetary nebulae are beautiful, but they are also brief. The Helix Nebula, one of the closest and brightest examples, has existed as a visible nebula for only about 10,000 years. In another 10,000, it will be gone, dispersed into space. Supernova remnants last longer. The debris from a core collapse supernova expands at thousands of kilometers per second, sweeping up surrounding gas and compressing it into a glowing shell. The remnant can remain visible for tens of thousands of years, gradually fading as the expansion slows and the gas cools. The Crab Nebula, the remnant of a supernova observed in 1054 by Chinese astronomers, is still glowing brightly today, powered by a rapidly spinning pulsar at its center. In another few thousand years, the crab will fade, its glow dimming until it becomes indistinguishable from the background interstellar medium. The pulsar will remain, spinning in the dark, but the nebula itself will be gone. The long-term fate of galaxies, once star formation stops, is a slow fade. The stars that remain will continue to shine, some for billions of years, others for trillions, but one by one they will exhaust their fuel. The massive stars will explode or collapse. The low-mass stars will swell into red giants, shed their outer layers, and become white dwarfs. The white dwarfs will cool, fading from white to red to black. The neutron stars and black holes will remain, invisible and inert, their only interaction with the universe coming from their gravitational pull. Galaxies will become darker, colder, emptier. The bright spiral arms, the glowing star-forming regions, the intense radiation from young massive stars, all of it will be gone. What remains will be a diffuse cloud of stellar remnants drifting through space, bound together by gravity but producing no light. The timescale for this process is measured in trillions of years. The longest-lived red dwarfs, the ones that formed in the early universe and are still shining today, will not exhaust their fuel for another 10 trillion years or more. Until then, galaxies will still contain living stars. But the trend is clear. Star formation is winding down. The supply of cold gas is dwindling. The universe is entering a long twilight, a slow transition from the bright star-forming era to a dark era dominated by dead stars and cold remnants. The galaxies will not disappear. They will just go dark, one star at a time, until nothing is left but the faint infrared glow of the last cooling white dwarfs and the gravitational ghosts of black holes that no longer interact with anything but space-time itself. And when the last star finally goes out, when the last white dwarf cools below the threshold of detectability, when the last pulsar spins down and fades into silence, the universe will enter a new phase, not an end exactly. There will still be matter, there will still be energy, but there will be no light, no fusion, no heat. Just the slow, patient decay of everything that once shone, waiting in the dark for whatever comes next. The universe is winding down. That is not a metaphor. It is not poetic license. The universe, in the most literal physical sense, is running out of usable energy. The stars are dying, the galaxies are fading, the expansion is accelerating. And at the end of it all, Trillions upon trillions of years from now, the universe will reach a state where nothing meaningful can happen anymore. No stars will shine. No galaxies will collide. No black holes will swallow matter. The cosmos will settle into a cold, dark, diffuse equilibrium where every region of space looks exactly like every other region, and the temperature everywhere approaches absolute zero. Physicists call this the heat death of the universe, and despite the name, it is not hot. It is the coldest, darkest, most featureless end imaginable. The term heat death is misleading. It was coined in the 1850s by William Thomson, later Lord Kelvin, who described the universe as running down like a clock. He was working out the implications of the second law of thermodynamics, the rule that says entropy, the measure of disorder in a system, always increases over time. A hot cup of coffee cools down. A broken glass does not spontaneously reassemble. Energy spreads out, dissipates, becomes less useful. The second law applies to everything, including the universe. And if entropy always increases, then eventually the universe will reach a state of maximum entropy. A state where all the energy is evenly distributed, all the temperature differences have been erased, and nothing can happen because there are no gradients left to drive any process. That is heat death. The end of all activity, not because the universe runs out of energy, but because the energy becomes so evenly spread out that it cannot do anything anymore. Katie Mack, an astrophysicist who has written extensively about the end of the universe, points out that heat death is not actually a hot phenomenon. The name is a historical artifact. What heat death describes is the opposite of heat. It is the big freeze, the big chill. The moment when the last usable energy gradient disappears and the universe becomes a uniform, featureless void at a temperature barely above absolute zero. Not quite absolute zero, because reaching absolute zero would violate the third law of thermodynamics. But close enough that the difference does not matter. Close enough that nothing moves, nothing changes, and nothing ever will again. The timeline for heat death is almost incomprehensibly long. The current age of the universe is about 13.8 billion years. That is a blink. The processes that will lead to heat death take place over timescales measured in tens of billions, hundreds of billions, trillions, and eventually numbers so large that standard notation breaks down and you have to start writing them as powers of 10. In about 100 billion years, the most distant galaxies currently visible from Earth will have receded beyond the cosmic horizon, their light stretched so far by the expansion of space that it can no longer reach us. The observable universe will shrink to just the local group and whatever galaxies remain gravitationally bound to it. In about 1 trillion years, the last stars will form. After that, no new stars will ignite. The universe will have exhausted its supply of cold gas, and star formation will cease forever. Once star formation stops, the universe enters a long twilight. The stars that are already burning will continue to shine, some for billions of years, others for trillions. The smallest red dwarfs, the faint stars that weigh only a fraction of our sun's mass, can remain on the main sequence for 10 trillion years or more, but eventually even they will run out of fuel. One by one, the stars will go out. The massive stars will explode as supernovae or collapse into black holes. The lower mass stars will swell into red giants, shed their outer layers, and become white dwarfs. The white dwarfs will cool, fading from white to red, to brown to black, until they no longer emit any detectable light. By about 10 trillion years, the last ordinary star in the universe will have exhausted its fuel. The night sky, from any vantage point in any galaxy, will be dark. No new light will be generated. The universe will enter what cosmologists call the degenerate era, a period dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Those remnants are not eternal. White dwarfs, the cooling embers of stars like our Sun, will continue to radiate away their stored thermal energy for tens of billions of years. Eventually, they will cool below the point where they emit any light at all, becoming black dwarfs. Cold, dark lumps of carbon and oxygen drifting through space, no longer interacting with the universe in any meaningful way except through gravity. Black dwarfs do not exist yet. The universe is not old enough. The oldest white dwarfs, formed more than 13 billion years ago, are still glowing faintly in the infrared. But give it time. In another 100 billion years, the first black dwarfs will appear. In a few 100 trillion years, most of the white dwarfs in the universe will have cooled into invisibility. And then there is proton decay. This is speculative. No one has ever observed a proton decaying. Protons, as far as we can tell, are stable. They do not break apart on their own. But some theories in particle physics, extensions of the Standard Model, predict that protons are not perfectly stable. They have a finite lifetime, an extraordinarily long lifetime, but finite. Current experiments place the lower limit on the proton's lifetime at about 10 to the 34 years. That is a 1 followed by 34 zeros. The universe is only about 10 to the 10 years old, so if protons do decay, the process is so slow that we have no hope of detecting it directly. But if protons decay, then ordinary matter, the atoms that make up stars and planets and everything else, will eventually disintegrate. A proton decays into lighter particles, typically a positron and a gamma-ray photon. The positron quickly annihilates with an electron, producing more gamma rays. Over trillions upon trillions of years, every proton in every atom, in every white dwarf and neutron star will decay. The stellar remnants will dissolve into radiation, scattered across the expanding universe. Ordinary matter will cease to exist. The timescale for proton decay, if it happens at all, is around 10 to the 40 years. That is a 1 followed by 40 zeros. Numbers this large do not correspond to anything in human experience. If you tried to count to 10 to the 40 at a rate of 1 number per second, it would take you longer than 10 to the 32 times the current age of the universe. The number is so large, it might as well be infinite, but the universe is patient. It has all the time in the world, literally, because it is the world. If protons decay, then by about 10 to the 40 years, every atom that ever existed will have broken down into gamma radiation and leptons. The universe will be empty of matter in the traditional sense. No stars, no planets, no rocks, no atoms. Just photons and a few wandering electrons and positrons, spread so thinly across the expanding cosmos that the odds of any two particles ever encountering each other are effectively zero. Black holes are the longest-lived structures in the universe. They do not decay the way matter does. They do not cool the way white dwarfs do. They sit in space, accreting whatever matter happens to fall into them, growing slowly over billions of years. But even black holes are not eternal. In 1974, Stephen Hawking published a paper showing that black holes emit radiation, not much. The radiation is extraordinarily faint, produced by quantum effects at the event horizon, where particle-antiparticle pairs spontaneously pop into existence, and one member of the pair falls into the black hole while the other escapes. The escaping particle carries away a tiny amount of energy, and over time, that energy loss causes the black hole to shrink. The process is called Hawking radiation, and for any black hole of stellar mass or larger, it is unimaginably slow. A black hole weighing 10 times the mass of the Sun has a Hawking temperature of about 6/1000th of a degree above absolute zero. That is far colder than the cosmic microwave background, the faint glow of radiation left over from the Big Bang. The cosmic microwave background currently sits at about 2.7 degrees above absolute zero. A black hole colder than the background radiation does not emit more energy than it absorbs. It grows rather than shrinks. But the cosmic microwave background is cooling. The universe is expanding, and as it expands, the wavelength of the background radiation stretches, which means its temperature drops. In about 100 billion years, the cosmic microwave background will have cooled below 1 degree. In a few trillion years, it will drop below the Hawking temperature of stellar mass black holes. At that point, black holes will begin to lose mass. The evaporation rate is slow. A black hole weighing 10 solar masses will take about 10 to the 67 years to evaporate completely. That is a 1 followed by 67 zeros. It is a timescale so long that it dwarfs the proton decay timescale by a factor of 10 to the 27. But it is not infinite. Black holes evaporate. The process accelerates as the black hole shrinks because smaller black holes have higher Hawking temperatures and radiate more intensely. A black hole weighing 1 solar mass evaporates faster than a black hole weighing 10. A black hole weighing 1 kilogram evaporates in a fraction of a second. The final moments of a black hole's life are dramatic. As the mass drops, the temperature spikes, the radiation intensifies, and the black hole explodes in a burst of gamma rays and particles. And then it is gone, no remnant, no trace. Just a flash of light spreading outward into the void. Supermassive black holes, the ones sitting at the centers of galaxies, take even longer to evaporate. The black hole at the center of the Milky Way weighs about 4 million solar masses. It will take roughly 10 to the 98 years to evaporate. The largest known black holes, the ones weighing tens of billions of solar masses, will take even longer, possibly 10 to the 100 years or more. These numbers are so large they lose all meaning. The universe is currently 10 to the 10 years old. The black hole era, the period when black holes are the dominant structures in the cosmos, will last until about 10 to the 100 years. After that, the last black hole will evaporate, and the universe will be left with nothing but photons and a handful of stable particles. Electrons, positrons, neutrinos, all of them spread so thinly across space that the universe is effectively empty. This is the photon era, the final stage before heat death. The universe contains only light and a few wandering particles, all of them moving through an expanding void that grows larger and colder with every passing eon. The photons, the remnants of black hole evaporation and proton decay, are redshifted by the expansion of space, their wavelengths stretched to kilometers, then light years, then distances so vast that they no longer resemble anything we would call light. The particles drift, separated by distances larger than the observable universe is today. Nothing interacts, nothing collides. The temperature approaches absolute zero, asymptotically, never quite reaching it, but getting close enough that the difference is negligible. The universe has reached thermal equilibrium. Every region of space has the same temperature, the same density, the same empty featureless structure. There are no gradients, no hot spots, no cold spots, no energy available to do work. Nothing happens, nothing can happen. The universe is dead in every way that matters. This is heat death. The ultimate consequence of the second law of thermodynamics, played out over timescales so long they make the lifetime of stars look like a sneeze. The universe does not end in a bang, it ends in silence. A slow fade to nothing, stretched across tens of billions of trillions of years, until the last particle has decayed, the last black hole has evaporated, and the last photon has been redshifted into irrelevance. What remains is not a void in the traditional sense. Space still exists. Time still exists, in principle, though time without change is a strange concept. The laws of physics still hold. But there is nothing left for those laws to act on. The universe has become a uniform, featureless expanse where nothing distinguishes one moment from the next, or one place from another. Maximum entropy, thermodynamic equilibrium, the end, except it might not be the end. Heat death is the leading scenario in standard cosmology, the one that follows most naturally from what we know about dark energy, the expansion of the universe, and the second law of thermodynamics. But it is not the only possibility. The future of the universe depends on assumptions we cannot yet test: the nature of dark energy, the ultimate fate of space-time. Whether the laws of physics themselves change over extremely long timescales. If any of those assumptions turn out to be wrong, the story changes. One speculative alternative is the Big Rip. If dark energy is not a constant, but instead grows stronger over time, the expansion of the universe could accelerate without limit. Eventually, the expansion would become so violent that it tears apart galaxies, then solar systems, then planets, then atoms, then even the fabric of space-time itself. The Big Rip is not gradual, it is catastrophic. The universe does not fade, it gets ripped to shreds. Current observations do not support this scenario. Dark energy appears to behave like a cosmological constant, a property of space that does not change with time. But the data are not conclusive. If dark energy strengthens, the universe could end in a Big Rip within a few tens of billions of years. That is soon by cosmological standards. Soon enough that the Milky Way Andromeda merger might not even complete before the universe tears itself apart. Another alternative is the Big Crunch. If the universe contains enough matter, or if dark energy weakens or reverses, the expansion could slow, stop, and then reverse. Galaxies would start moving toward each other instead of away. The cosmic microwave background would heat up instead of cool down. The universe would contract, collapsing back into a hot, dense state, eventually reaching temperatures and densities similar to the Big Bang. The Big Crunch is the time-reversed mirror of the Big Bang. Everything that expanded outward collapses back inward, ending in a singularity where the laws of physics break down and nothing can be predicted. The Big Crunch is not favored by current observations. The expansion is accelerating, not decelerating. But the possibility is not ruled out entirely. If dark energy is not what we think it is, if the universe has hidden mass we have not detected, the Big Crunch could still happen. Some cosmologists have proposed cyclical models where the Big Crunch is not the end but a transition. The universe collapses, reaches a point of maximum compression, and then bounces, expanding again into a new Big Bang. The cycle repeats indefinitely. Big Bang, expansion, contraction, Big Crunch, bounce, new Big Bang. Each cycle could last tens or hundreds of billions of years, and the universe could have gone through an infinite number of cycles before this one. Cyclical models are elegant. They avoid the uncomfortable question of what came before the Big Bang by proposing that there was no before. The universe has always existed, cycling through expansions and contractions, with no beginning and no end. The models are speculative. They require exotic physics that has not been observed, but they are not ruled out. Roger Penrose, a Nobel Prize-winning physicist, has proposed a different kind of cyclical universe called conformal cyclic cosmology. Penrose argues that in the far future, After all matter has decayed and all black holes have evaporated, the universe will consist only of massless particles traveling at the speed of light. For such particles, time does not pass. The concept of before and after loses meaning. Penrose suggests that this far future state could be mathematically identical to the conditions immediately after the Big Bang. The end of one eon becomes the beginning of the next, not through a bounce or a crunch, but through a conformal rescaling of space-time. The idea is deeply mathematical and difficult to test, but it offers a vision of the universe as eternal, passing through infinite cycles without ever truly ending. Another speculative idea is vacuum decay. The universe might not be in its lowest energy state. The vacuum of space, the empty nothingness that fills the gaps between particles, might be metastable, a false vacuum. If that is true, then somewhere, at some point, a region of space could spontaneously transition to a lower energy state. That transition would create a bubble of true vacuum expanding at the speed of light, destroying everything in its path. The laws of physics inside the bubble would be different from the laws outside. Particles would have different masses, forces would have different strengths. The universe as we know it would be annihilated, replaced by something fundamentally different. Vacuum decay is not predictable. If it happens, we would not see it coming. The bubble would hit us at the speed of light, and we would be gone before the first neuron in our brains could fire. The universe could end tomorrow, or in 1 trillion years, or never. There is no way to know. These alternatives are speculative. They are not the mainstream prediction. The data we have, the observations of distant supernovae, the measurements of the cosmic microwave background, the behavior of galaxies and clusters, all of it points toward an accelerating expansion and an eventual heat death. But science does not deal in certainties, it deals in models and probabilities, and the best explanation given the current evidence. The evidence could change, the models could be wrong, the universe could surprise us. What does heat death mean for meaning? That is the question no one wants to ask, but everyone thinks about. If the universe ends in a cold, dark, empty void where nothing happens and nothing can happen, what is the point? Every star that ever shone, every galaxy that ever formed, every planet that ever harbored life, all of it leading to nothing. Heat death is the ultimate nihilistic punchline. The cosmos builds complexity, organizes matter into stars and galaxies and living things, and then it all decays back into featureless equilibrium. The second law wins. Entropy increases, everything falls apart. But that is looking at it from the wrong angle. Heat death happens trillions of years in the future. Trillions. The universe right now is young, active, full of stars and galaxies and structure. Life exists, consciousness exists, you exist. The fact that the universe will eventually reach heat death does not erase the fact that right now, in this moment, things are happening, stars are forming, planets are orbiting. Light is traveling across billions of light years, carrying information about the history of the cosmos. The universe is not dead yet. It will not be dead for an incomprehensibly long time, and in the meantime, there is everything. Every sunrise, every galaxy, every discovery, every moment of wonder at the fact that the universe is comprehensible at all. The universe does not owe us a happy ending. It does not owe us permanence. The fact that stars die does not make them less beautiful while they shine. The fact that galaxies will eventually fade into darkness does not diminish the light they emit now. Heat death is not a tragedy. It is a consequence. The universe is playing by the rules of thermodynamics, and those rules do not care about meaning or purpose, or whether we find the ending satisfying. But the universe gave us time. Billions of years in the past, trillions in the future. Time to explore, to understand, to build, to create. Time to look up at the night sky and ask what it all means. That is not nothing. That is everything. And maybe, just maybe, there is something we are missing. Some piece of physics we have not discovered yet. Some loophole in the second law of thermodynamics that allows complexity to persist even in a universe approaching equilibrium. Some mechanism by which intelligence, if it survives long enough, could find a way to keep going even after the last star dies. It sounds like wishful thinking, and maybe it is, but science has a long history of discovering things that seemed impossible. The universe has surprised us before. It could surprise us again. Heat death is the end the equations predict, but the equations are not the universe. They are our best attempt to describe it, and descriptions can be wrong. The future is not written. It is extrapolated from the present using models that depend on assumptions we cannot fully test. The universe is under no obligation to follow our script. It has been breaking expectations since the first supernova turned out to be brighter than it should have been and revealed that the expansion is accelerating. Every time we think we have the universe figured out, it hands us a new mystery: dark matter, dark energy. The impossibly early galaxies seen by the James Webb Space Telescope. The universe does not make it easy, so here is the glimmer, not hope exactly. Hope implies optimism, and the universe is not optimistic or pessimistic. It just is, but a glimmer nonetheless. The recognition that we do not know everything, that the future is longer than we can imagine and stranger than we expect. That heat death is a prediction, not a certainty. And that in the meantime, in this brief flicker of time when stars still shine and galaxies still collide and life still asks questions, we get to be here. Witnesses to a universe that is vast and old and beautiful and utterly indifferent to whether we understand it. The fact that we try anyway, the fact that we look up and wonder and build telescopes to see farther and deeper and earlier, that is the only meaning the universe is ever going to give us, and maybe that is enough. We began with a flash. A universe smaller than an atom, expanding into everything. Hydrogen cooling in the dark, gravity pulling it together, the first stars igniting like matches, struck in an endless void. From that beginning, galaxies assembled. Spirals and ellipticals and irregulars, 2 trillion of them scattered across a cosmos so large that light takes billions of years to cross it. We traced the life of our own galaxy, the Milky Way, a barred spiral containing hundreds of billions of stars, most of them invisible, most of them fated to burn quietly for trillions of years before fading into darkness. We found the black hole at its heart, 4 million solar masses of collapsed spacetime, quiet now but once blazing as a quasar, shaping the galaxy around it through feedback and radiation. We watched galaxies collide, tearing each other apart, triggering starbursts, merging into ellipticals, building the largest structures in the universe, one violent encounter at a time. And then we looked forward, into a future where the expansion accelerates, where galaxies recede beyond the horizon, where the Milky Way and Andromeda merge and sit alone in an ever-darkening void, where the last stars exhaust their fuel, the white dwarfs cool into black dwarfs, the black holes evaporate into radiation, and the universe reaches a state of maximum entropy. Heat death, the end of all gradients, all activity, all light. That is the story the equations tell. From first light to final darkness, 14 billion years of history, trillions of years of future, all of it leading to silence. And yet here we are. In the brief window, when stars still shine, when galaxies still collide, when the universe is young enough to be interesting and old enough to be understood. The fact that it ends does not erase the fact that it happened. The universe gave us time, it gave us light. It gave us the tools to look back at our own beginning and forward to our own end. That is not tragedy, that is the story.